activating sessions that filled the first day of Physics Pulse, dedicated to the fascinating world of physics. So, let me ask a few questions um, to the students. So, first of all, and I need honest answers from you all. So, did you find the lectures engaging and thought provoking? Yes, good. And were the hands on training and experiments illuminating and enjoyable? Very good. So, is there anything specific you would like to see again or see more? Anything specific? No. Okay. So, it's good to learn that we could inspire you to the world of physics, because cultivating physics makes you rational, mathematically proficient, a critical thinker, and gives you a problem solving outlook. The take home message for Physics Pulse is that a flexible mind and a logical brain can excel in any field. So you can see a glimpse of it from yesterday, and today also you will be absolutely certain about it. So today we have with us Professor Dr. Bimal Kumar Sarkar, Professor, Department of Physics and Professor in charge, Academic Affairs Examination of Adamas University. So may I request Professor Sarkar to come up to the stage and welcome the audience.
Good morning to everybody. So this is very nice moment. Again, we are welcoming you, even though this is the second day. But what should we go for welcoming again? If we see today's event, yesterday it has been started, Physics Pulse 2023, Pulse. Pulse means everything is very vibrating. So every day we will welcome all of you. Now, thing is that why Physics Pulse? So if we see from very beginning, so sometimes can I speak in Bengali also? Any problem to you? Okay. So যদি তোমাদের জিজ্ঞেস করি একদম প্রথম দিক থেকে একজন পাগল ফিজিস্টের নাম বলো। এনি নেম? অ্যালবার্ট আইনস্টাইন। সবাই বলবে আচ্ছা। নিউটন কে বললে? এক্স্যাক্টলি। নিউটন কিন্তু মস্ত বড় পাগল ছিলেন। কারণ কি যখন he was sitting beneath the tree, apple coming down, তো উনি দেখে ভাবলেন যে এটা প্রত্যেকে আমরা জানি আমরা যে আপেলটা মাটিতে নিচে পড়ে গেল। এবার উনি ভাবছেন নিচে পড়লো কেন এটা? প্রত্যেক লোককে উনি জিজ্ঞেস করছেন। He is asking everybody, why apple is coming down? Why? Everybody is answering him, this is mad person. আরে আপেল তো নিচেই আছে, উপরে যাবে নাকি? মানে এটা দেখে লোকে তাকে পাগল বলতে শুরু করে দিল। তারপরে ব্যাপারটা সবাই আমরা জানি যে কি হিস্ট্রি। তো দেখো মানে এই যে ইনোভেশন, এই যে মোটিভেশন, এগুলো দিস আর ভেরি ইম্পর্টেন্ট and it is vibrating. Now we are talking about gravitational wave, those things. You just think for the transformation from that Newtonian gravitation to now we are talking about what we are talking about gravitational field, gravitational wave, etc. So this transformation contributed from every person, right from Newton to and latest every physicist. So why I am giving this example, that physics is the subject where we need loving this subject, we need the passion. যদি কারো এগুলো থাকে তাদেরকে ফিজিক্স পাস করে বা ফিজিক্স নিয়ে পড়ার পর কখনো ভাবতে হয় না যে স্কোপটা কি, আমি কোথায় কি করব। যদি আমরাও তো আজকে এই জায়গায় তোমাদের সঙ্গে কথা বলছি, যোগ্যতা আমরা অর্জন করছি কেন? আমাদের ফিজিক্স নিয়েই পড়েছি। Any query? So you see that to understand everything, basically what we see around us, the physical world, to be explored with the help of knowledge what we can find from physics. And really, if we find knowledge from physics, even though in that case, we don't need to think regarding our also next establishment and in our life, what we'll do. So most important thing is we have to be very much lover of physics, and we have to understand everything. For example, we are talking about sometime from our childhood, we just play with different part of the nature. Say, for example, a very small child, he or she is jumping on the earth, and he is giving force to the earth, and then he jump up. This thing is going on. So the child is playing. Very nice thing that the child is playing. Really, is it so? Child is playing? No, the nature is playing with the child. So what exactly what I mean? That means that when something is there, it needs two-way interaction process. So we can think in this way also. The child is not playing, but the nature is playing with the child. So understanding all these things, we need the in internal meaning. Sometimes we can think that, okay, if we think the internal meaning of all these things, what it will give us. What is it enough to give us the professional establishment? Sometimes we may be also thinking in that way. But thing is that no, if someone is very much involved in any subject, that obviously that will give return to us. Same to physics also. If you really like it, you love it, then you can pursue the process of knowledge gathering in physics. Number two, another very nice thing for physics is that if you see different scientific field, different aspects, even there, physics can solve the problem in other field also. Lot of examples are there already. I am going to that part. I'm not going to that part to explain this. You know all these things. Many physicists involved in biological science, they can explore many things from biological science also. Many physicists involved, you believe me, the worldwide, the topmost, the topmost programmer and computational work involved in the process, the topmost programmer, they are from physics background. Now, question is that why so? Because if you really become a good physicist, some criteria is that you should be very rationalized in thinking. You should be very good analytic person. You should have very good observation. If it is there, it is not matter whether you are learning engineering, you are going to technology, you are going to other professional fields. I giving another example, then I'll end my talk. Even nowadays, people from other fields, people from other fields, one of my friends, he is from the background from political science. He was discussing many things regarding political scenario in the world. I simply asked one question to him. He is a very big guy in political science. I asked him that, sir, can you tell me one thing, what I observe? It is the observation from physics point of view, that 20 years back, the political center, the political center of mass was around Western country there. Now the political center has been changed to Eastern or East Asia, in the region of China, those things. So this shifting from one point to another point, is there any trajectory through which this epicenter of this political world is shifting? He was get very surprised. He told me, you are not, you don't seem that you are not a person from political science. So I have said from the point of view, what I understand, what I learned from physics, from that point of view, I have told this. But he has accepted this with very innovative idea, that you have given a very innovative idea. And believe me, then approach to me, can we do some work on this matter? So you see here, then I just simply given some conception, sir. It is thing is that how we can go this, I can give some example. So for example, how we define the first of all the particle center. Maybe some criteria, some parameters are there. What are those parameters that you decide? Maybe 8, 9 parameters are there. Now, if the status 20 years back is given in some kind of 9-dimensional space as a state function there, and now what we are now, we can put the state function there. So here, obviously the system is also nothing but to follow the optimized path. So in this way, we can study this thing. Oh, great idea you've given. He just accept me in this way. See that I can speak something from physics point of view to political science also. Even if you see nowadays, if the economical status of the world, there are also many things are there. You can give the idea from physics to economics also. And so what I give in this example, because it means that if really you become a good physicist, nobody can resist you. Nobody can stop you from any kind of problem solving capability that I'm telling you. And really, if somebody is very much eager to learn in physics, I believe that he can do anything in any field also. This is my last conclusive word to you. And I believe that you also like physics, and you also better if you go to this subject. Don't think that I'm getting biased, I'm telling to you. It is my feeling, something like this. Because ultimately, you need very analytical mind and rationalized thinking. That comes from physics. That's all. Thank you very much. Welcome you again.
Thank you so much, sir. Thank you for explaining that if we have a base in physics, we can do whatever we want. So, um, let us begin today's first session, which includes a distinguished lecture by Dr. Manik Bonik from SN Bose Center for Basic Sciences, followed by another talk by Dr. Biplab Sarkar, Chief Medical Physicist of Apollo Hospital. The session will be chaired by Professor Dr. Dipankar Bhattacharya, Pro Vice Chancellor, Research and Innovation, and Dean of School of Basic and Applied Sciences. I would request Professor Bhattacharya to come up to the stage and take over the session.
Thank you. Good morning, all of you. And so in this session, the first talk will be on the nature is non-local ultimately. So it's mostly related to quantum mechanics. But I'm certain Dr. Manik Bonik will explain it really lucidly to you so that you can understand what is going on. So before that, I would like to introduce Professor Dr. Manik Bonik. So Dr. Bonik is an accomplished physicist and currently serves as an associate professor in the Department of Physics of Complex Systems at the SN Bose National Center for Basic Sciences in Kolkata since June 2022. With an impressive academic background, Dr. Bonik has been making significant contributions to the field of quantum physics and information theory. So you can understand that it's basically an interdisciplinary area where he is working on. It is with physics, fundamental part of physics, which is quantum physics, quantum mechanics, and as well as information And you will find later that he also specialized in the area of mathematics also. So you have to learn everything. Before joining SN Bose, Dr. Bonik held the position of assistant professor at the Indian Institute of Science, Education and Research, commonly known as ISER, at Tiruvananthapuram from February 2020 to June 2022. Prior to that, he was a DST Inspire faculty member at SN Bose Center from April 2018 to February 2020. Dr. Bonik also gained valuable research experience during his postdoctoral fellowship at the Institute of Mathematical Sciences, Chennai, from October 2015 to January 2018. His research interests span various integrating aspects of quantum physics, such as quantum information theory, quantum communication theory, quantum thermodynamics, causality in quantum world, and quantum foundations. So they're pretty heavy words, but hope you will understand it really well. Dr. Bonik's work has earned him recognition and several prestigious awards and fellowships and grants. Notably, he received the Startup Research Grant from SARB in 2021 and the Chanakya Postdoctoral Fellowship from iHub Quantum Technology Foundation in the same year. Earlier, he was honored with the Inspire Faculty Award. With his passion for unraveling the mysteries of quantum phenomena, Dr. Bonik continues to inspire and contribute to the advancement of quantum science. So I welcome Dr. Bonik, and the stage is all yours.
So how to I should use this mic, no? Color mic should be okay. How to make it full screen? This, no? Okay, so good morning, everyone. And first of all, I'd like to organizer to invite me here and such a nice introduction. So this is the title of my talk. The nature is non-local ultimately. So for student, which word is not understand in this title? The is you understand, no? Nature you understand. Non-local. And then I emphasize ultimately. I'll come to that. So again, before going to this technical part, I'm really happy to talk in front of you. And my teacher is also here when I was doing my bachelor's, master's under from Jadavpur University. My teacher is also present here. So how many of have you seen this picture? Who is this guy? And who is this guy? So what Einstein is saying, I am at any rate, I'm convinced that he does not throw dice. He means God. Here by God, Einstein means, Einstein was mainly atheist. By God, he means nature. That nature is not random. What was Bohr's reply? Einstein, stop telling God what to do. Okay. Stop telling God what to do. Means how nature should be, why you will go on. How nature is, you will learn it, will take it. So you understand there was a debate going on between Einstein and Bohr. So who is correct, you think? Let us see. Because we are physicists ultimately. Why you think Einstein is correct? Because you like Einstein, no? Physics should not go in this way. We should come up with some experiment. And from experiment, we will try to see who is correct. And how many of have you seen this guy? Probably very less. He's another scientist. We will come to his point. He actually come up with a way to design an experiment that will tell who is correct, whether Einstein is correct or whether Bohr is correct. So apparently it was a kind of philosophical question. What is going on? And this guy will come back to this guy who is he come up with a innovative technique to design an experiment from which we can test who is correct, Einstein or Bohr. Okay, so do you know that last year Nobel Prize Physics was given to 3 guys? And these are the 3 guys who have performed the experiment what the other guys has designed. His name is John Stuart Bell from Ireland. He actually designed an experiment, and these 3 guys, Professor Alan Aspect, John F. Clausier, and Anton Zeilinger, they actually performed the experiment to test that who is correct, Einstein or Bohr. That's why Nobel Committee says for experiment with entangled photon, what is entangled photon? These peculiar things. Okay, establishing the violation of Weyl inequalities and pioneering quantum information science. For this reason, they are given the Nobel Prize last year. So of course, there are lots of very difficult words. We'll not go in details, but intuitively we try to understand what are the question was there. Why resolving that question was so important that it was given Nobel Prize for that. That we try to understand from a mainly historical point of view. Okay. If you have some technical question, you can ask during my talk also and after my talk also. Okay. And if I go sometimes in my speech, I go to English and Bengali, is it fine? Okay, fine. So how many have you heard of the name George Bernard Shaw? Okay, why he is famous for? He also a Nobel laureate, no? He got the Nobel Prize for literature. Not only that, he's also got the Oscar. How many of you know that he also got the Oscar for screenplay? So we start with a dinner speech by George Bernard Shaw in honor of Albert Einstein. How this video will open?
George Bernard Shaw, speaker at the Joint British Committee of
এটা কি সাউন্ডটা এই সাউন্ডটা শোনাতে চাইছে এই ভিডিও সাউন্ডটা so please this is a 2-minute talk you just listen it I'll then explain acha din if sound is less you can also read the slide
George Bernard Shaw speaking at the Joint British Committee Authors' Day dinner in London in honor of Professor Einstein. There is always a great deal to concede. If you take the typical great man of our historic epoch, and suppose that I had to rise here tonight, suppose the toast of Napoleon. Well, undoubtedly I could say many very flattering things about Napoleon. But the one thing which I should not be able to say about him would be perhaps the most important thing. And that was that it would perhaps have been better for the human race if he had never been born. Napoleon and other great men of his type, they were makers of empire. But there is an order of men who get beyond that. They are not makers of empires, but they are makers of universe. And when they have made those universes, their hands are unstained by the blood of any human being on earth. Ptolemy made a universe which lasted 1,400 years. Newton also made a universe which has lasted 300 years. Einstein has made a universe, and I can't tell you how long that will last.
Okay, so what George Bernard Shaw is telling? He's telling, okay, if মানে আজকে যদি ওনাকে বলছে আমাকে যদি বলা হয় নেপোলিয়ন সম্বন্ধে কিছু বলতে, তাহলে আমি অনেক ভালো ভালো কথা বলতে পারি, কিন্তু যেটা সবচেয়ে হয়তো বলা আমার ঠিক হবে কিন্তু উচিত নয়, যে সবচেয়ে ভালো হতো মানব সভ্যতার জন্য যদি নেপোলিয়ন জন্ম না নিত। কেন বলছে এই কথাটা? কারণ ও এম্পায়ার তৈরি করেছে অনেক যুদ্ধ করে, আর যুদ্ধ মানে প্রচুর লোক মারা যায়, সেই জন্য এই কথাটা মিন করতে চাইছে। বলছে ওরা এম্পায়ার তৈরি করে, সাম্রাজ্য তৈরি করে, এম্পায়ার তৈরি করে, প্রচুর লোককে মেরে তাদের হাতে রক্ত লাগে, কিন্তু দেয়ার ইজ এ অ্যানাদার কাইন্ড অফ ম্যান হু আর ইন ডিফারেন্ট লিগ। তারা এম্পায়ার না, একটা ইউনিভার্স তৈরি করে, বাট কোথাও হাতে কোথাও রক্ত লাগাতে হয় না। টলেমি ও একটা ইউনিভার্স তৈরি করেছে, সেই ইউনিভার্সে 1400 বছর ছিল। তারপর নিউটন আরেকটা ইউনিভার্স তৈরি করেছে, সেটা 300 বছর ছিল। তারপর আইনস্টাইন আর একটা নতুন ইউনিভার্স তৈরি করেছে, এবং আমি জানি না কতদিন এটা থাকবে। এটা হচ্ছে ওর টকের বিষয়টা। আজকে যাই না, আজকে হয়তো এটা দেখো 1930 সালে জর্জ বার্নার্ড শো এই টকটা দিচ্ছে। আজকে হয়তো যদি জর্জ বার্নার্ড শো বেঁচে থাকতো, আজকে হয়তো নেপোলিয়নের বদলে অনেকের নামই বলতে পারতো, যাদের ও মানে এই যারা এই কালপ্রিট হিউম্যান সভ্যতার জন্য, যাদের জন্য প্রচুর যুদ্ধ বিগ্রহ প্রচুর কিছু হয়েছে। কারণ এটা 1930 সাল, তারপর সেকেন্ড ওয়ার্ল্ড ওয়ার আমরা দেখেছি, যেখানে প্রচুর হিউম্যানের ক্ষতি হয়েছে। বাট সেটা আমাদের আজকের বিষয় নয় বোঝার। আওয়ার মেইন গোল ইজ টু আন্ডারস্ট্যান্ড হোয়াট দিস last three lines. Our aim is to understand this last three lines. What is mean by that? That is our aim. Okay, how many of heard you Ptolemy's universe? Very simple. What Ptolemy used to believe that our earth is the center of the universe, and everybody rotate around this. This is called geocentric or earth-centric universe. Is it correct? So, but you see, today you know it is not correct, but it was when Ptolemy was telling. It's much before BC also. At that time, our knowledge was that Earth is in the center of the universe and everything rotates around that. That was the Ptolemy's universe, and it lasted for nearly 1400 years. When people used to believe that yes, our nature is like that. When it was contested, when people see new observation, like Nicolas Copernicus, Tycho Brahe, Bruno, Galileo, they observe something regarding the stars, all these things, and they come up with a model. No, it should not be the case. The model should not be a earth-centric model. It is universe is something different. So then Galileo discovered what is called this Durbin, no, telescope. He observed lots of new stars as well as planets. And finally, all this observation leads us to a very famous theory established by Newton. That is the, sir, just few minutes back, sir was talking about the story of Apple. And this actually helps Newton to build his very famous gravitational theory. That if there are two bodies, they exert force to each other, and the force law is given by this. And this explains why this all the planetary motion, everything. This is so useful. Okay. So gravity in Newton theory, however, appear to non-local force and allow instantaneous signaling. Let me try to explain it. So now let's say this is a massive particle. It has gravity, no? So it has gravity is everywhere. No, it is maybe if I go to large distance, its effect will reduce, but it is there still. Okay, now I move this object. So gravity will change. How much time it will take? Let's say you are at Alpha Centauri. Alpha Centauri is large, huge distance, no? So even I send this light, it is a powerful laser, it will take 4 years nearly because it is 4 light year away. So it will take 4 years to reach that light to Alpha Centauri. Now let's say your friend is sitting at Alpha Centauri and you are moving this object, massive object. So this gravity will change. So when he will understand, yes, you are moving it. But Newton theory say, no, it is instantaneous. If you just do it, instantaneously it will affect it. That is called non-local, or instantaneous signaling is allowed in Newton theory. Clear? It is not local, it is instantaneous, non-local. And Newton was not happy with that. That gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and the through which their action and force may be conveyed from one to another, is to me so great an absurdity. Because how we have to explain it, how this is happening. But Newton theory cannot explain it. So that's why he's saying it is absurdity. We should be able to explain that. That I believe no man who has in philosophical matter of competent faculty of thinking can ever fall into it. Gravity must be caused by an agent acting constantly according to certain laws. But whether this agent be material or immaterial, I have left to the consideration of my reader. So Newton cannot answer this question. If you and this quotation I am taking from his book, this famous book Principia. He's saying, okay, how it is happening? Is it instantaneous or it is gradually happening step by step? That I left to my readers. They have to further do research, all these kind of things to explain it. So now it is a Newton's universe. It is different than Ptolemy's universe. So Ptolemy's universe has been broken. It was not our universe is not a Earth-centric universe. It is a new kind of universe, Newton's universe. But Newton's universe, what is the important fact? It is instantaneous signal you can send. That is the important part of Newtonian gravity. Now, nearly after 300 years, Einstein came into this picture. Einstein said, no, nature is local. Nothing can propagate instantaneously. If I have to send any information, any signal, I am talking to you. The sound is going to your ear, you are listening it. No, but it requires some time to go this sound wave from here to your end. He's saying it is not for sound, anything, even for light. It cannot be instantaneous. There is a upper limit. And what is the limit? The speed of light in vacuum. This is we call special theory of relativity. That means Einstein makes our universe local. That any information, any effect should travel in a finite speed, and the upper speed is speed of light in vacuum. This is called principle of locality. One of the consequence of special relativity is that if causality to be preserved, no information signal or material object can travel faster than light in vacuum. Okay, you should ask this question, why will accept it? You should ask it. You can, one simple answer is, Einstein tells that's why I will accept. Will you take this answer? Einstein might be wrong, no? Now, we'll not discuss it, but I'm telling you what will happen. If I can instantaneously signal, no, some peculiar things I can do. I can go back to my past and I can kill my grandfather. So my grandfather is killed, so my father will not born. That means I will not born. Now, but how it is happening? This is called grandfather paradox. If it is instantaneous signal, this kind of paradox we can create. So that's why we are taking this step. It is not that Einstein is telling. Einstein is saying that if you take that, if you don't take it, I can create such a paradox. That probably we will not take. No, that is very puzzling paradox. I am killing my grandfather, then how my existence will come? It's a logical paradox will come. Then, so Einstein special theory of relativity is 1905. After 10 years, Einstein gives the general theory of relativity. It is called general theory of relativity. And later Einstein succeeded in producing an alternative theory of gravitation, general relativity, which obeys the principle of locality and provides a material account of how gravity works. Means the question what Newton posed in his Principia, Einstein addressed this question that yes, gravity also propagates with finite speed. Nowadays we call it gravitational wave. If I do something here, if two black holes collide, it creates a ripple in space-time. And these ripples also propagate with finite speed. That speed also cannot be more than speed of light. So now we know gravity is not non-local. That's why we are in a new universe. So Einstein universe as a Newton universe Einstein broke. It was instantaneous signaling. Einstein said no, it is also a local universe. Is it clear so far? Great. Okay, so here I quote something. Okay, that is not for the time being is important. We'll come because this talk probably I have given to other audience also. For that I quoted this. It has some more deeper philosophical implication that I am not going to discuss here. So now in 19th century, a new mechanics come. It's called quantum mechanics. So why a new mechanics required, first of all? What do you, if somebody asks your let's say your brother or sister who is in class 4 or 5, he asks you a question, why a new subject is required? What will be your answer? Not, okay, learn many things we can do, no. Actually, the problem is there are new experiment was observed that cannot be explained by old language. So few experiment was observed in early 20th century or late 19th century that cannot be explained by our old language. By old language, I means if it is a particle, then it is Newtonian language, Newton 3 laws, or if it is a wave, we have a theory that is called Maxwell theory that cannot explain this new phenomena. Some of these phenomena are called double slit experiment, black body radiation, photoelectric effect. For the photoelectric effect, actually Einstein got this Nobel Prize. Stern-Galag experiment, Compton scattering, and so on. Lots of experiment, new experiment has been observed that cannot be explained by this old language, old mechanics, that is this Newtonian mechanics and Maxwell wave mechanics. Through that, we cannot explain those new experiments, new fact. So this motivates a new subject. And this subject is not built on one day. Early 20th century, lots of scientists worked together effortlessly day and night, and nearly after means their 20 years effort give birth to a new subject called quantum mechanics. Lots of scientists contribute there. Max Planck, Niels Bohr, Einstein, Dirac, Pauli, Heisenberg, Schrödinger, Wigner, von Neumann, lots of and so on. Their 20 years effort build a new mechanics that's called quantum mechanics. So there are two. First, initially there are different kind of description. One is called matrix mechanics, some mathematical description by Heisenberg, and then what is called wave mechanics, so by Schrödinger, and then Paul Dirac has actually shown that these are equivalent. And same thing, different description, different way you are describing same things. So both matrix mechanics and wave mechanics will give you the same prediction. And this is these two very famous books, one by Dirac, The Principle of Quantum Mechanics, and one by probably von Neumann, Mathematical Foundation of Quantum Mechanics. So now we have quantum mechanics. We have a very good theory to explain all the phenomena regarding nature, all phenomena, molecular, atom, particle physics, everything. Apart from, so far there is one aspect we cannot explain. For last 100 years, people are trying. still we don't have a good theory that what is the theory of quantum gravity. That is not very well understood. Some progress is there, but it is not yet understood. So apart from gravity, every physical phenomena is well understood by this quantum mechanics. So quantum mechanics work perfectly for all practical purpose. Sometimes it is coined as FAP, F-A-P-P. For all practical purpose, quantum mechanics works good. So now if you say, okay, sir, can you try to teach us quantum mechanics? Yes, it is possible. It will take some time. But if we see no quantum mechanics, you will see, okay, Newtonian mechanics is very, very intuitively clear. What it says, if something is in rest, it will remain in rest. If it is in some velocity, it will keep moving with the same velocity. This is our called first principle, no? First law. Second law says, if you apply external force, its velocity will change, and rate of change of velocity is proportional to force applied. Second law. Third law says, action reaction equal and opposite. A very, very physical statement, no? But if you ask me to start with quantum mechanics, I cannot start in this way, unfortunately. I have to say, oh, there is some Hilbert space mathematical, very peculiar mathematical structure we have to take. But if we take this, all this mathematical description, beautifully all these phenomena we can explain. So quantum mechanics explain all these phenomena, but it doesn't tell us what is the underlying story. It is very mathematical. That should not be. Physical theory, a theory of physics should have physical motivation. Or it should be, we should able to say it in physical word. But quantum mechanics is not like that, unfortunately. So that's why we are asking question, wasn't there more to physics than FAP? Okay, for all practical purpose, quantum mechanics is working good, but shouldn't we ask more deeper question? What it is actually telling us about the nature? What is the underlying story? Underlying story means I say, okay, no information can travel faster than light. You say, okay, why I will believe that? Then I give you a story that if you don't believe it, I can go back to my past, I will kill my grandfather, and such a logical paradox will create. Can I give such a story for all these mathematics of quantum mechanics? This was some question people were bothered. This is called, these are questions about quantum foundation. At the end of the day, after all the wave functions has been calculated and probabilities plotted, shouldn't quantum mechanics have something coherent to say about nature? And this question was bothering lots of father of quantum mechanics. You see, this is a very famous picture, 1927 Solvay conference. Probably more than 20 person in this figure are Nobel laureate. She is Marie Curie. She actually got Nobel twice, no? Once in physics, once in chemistry. Her husband was also a Nobel laureate, as well as her daughter was also a Nobel laureate. So a Nobel family actually. So this kind of questions, that what quantum mechanics tells us, the father of quantum mechanics used to discuss all those questions in different conferences. And this Solvay is one particular place in 1927. This is the Solvay conference. So, and that creates the debate between Einstein and Bohr, that what quantum mechanics is telling to us. This very random kind of things, probabilistic nature. Should a fundamental theory of nature be random? Einstein used to believe, no, it should not. On the other hand, Bohr used to say, no, this is the final theory of nature. So the debate was going on. So now in 1935, Einstein, he was in Princeton at that time. Yeah, he was in Princeton, along with his two colleagues, Podolsky, Boris Podolsky and Nathan Rosen. They actually write a beautiful paper that, okay, there is some problem in quantum mechanics. We'll try to intuitively try to understand. And you see, look into carefully. The paper, it is in Physical Review, published in May 13, 1935. On the other hand, before its publication, nearly 1 week before, at that time, New York Times make a news, Einstein attacked quantum theory. Colleague, a scientist and two colleagues finds it is not complete, even though correct. And Einstein was not happy with that. That okay, a paper is not yet published. Why a newspaper journal should make it popular? Okay, that is a different story. That's another aspect. We are not going there. This is the Einstein reaction to this story. Any information upon which the article Einstein attack quantum theory in your issue on May 4 is based was given to you without authority. It is my invariable practice to discuss scientific matters only in the appropriate forum, and I deprecate advance publication of any announcement in regard to such matter in the secular press. Okay, that is why he was not happy with that. That is a different story. Some other time we can discuss those. But okay, how they are trying to attack? So okay, we have a physical theory. How good the theory is? That is a very good question. So by good, how good, what we mean? First of all, two questions we can ask. How correct the theory is? What do you mean by how correct the theory is? So theory will give some prediction. So Newton's law gives some prediction that if I have that much mass, if I apply that much force, then it should be there after few times second. This is a prediction we are doing by mathematics, following Newton's law. And then we real life, we go there and we'll see whether our prediction is matching with the real life experiment. So the correctness of a theory is tested with the experiment. Clear? So this is one first question, important question about a theory. Second question is the description given by theory complete? I'll come back to it. What Einstein and his colleagues saying, it is the second question that we wish to consider here as applied to quantum mechanics. So quantum mechanics is correct. That was not their problem. But is it a complete theory? That question we are trying to address in this paper. That if we are telling in all this slide, what I will, if it is in quotation, then I am taking it from their paper. Whatever, now the question is, what do you mean by a complete? Now what Einstein and his colleagues are telling, whatever the meaning assigned to the term complete, the following requirement for a complete theory seem to be necessary one. They are saying, okay, we will say a theory is complete. Every element of physical reality must have a counterpart in the physical theory. Is it clear? Is it clear, the statement? But when I was reading, it was not clear to me. What does it mean? Every element of physical reality must be a counterpart in the theory. This is their requirement of completeness. Then you should ask, no, it is not clear. What do you mean by physical reality? That we have to first tell what is meant by physical reality. Otherwise, how this line is clear? They are saying, I will say a theory complete if this criterion is satisfied. Every element of physical reality must have a counterpart in the physical theory. Because Einstein is very much, means a very deep thinker. He knows whenever someone will read his paper, he will immediately ask the question, what do you mean by physical reality? That's why next line he describes. A comprehensive definition of reality is, however, unnecessary for our purpose. We shall be satisfied with the following criteria, which we regard as reasonable. Now, what they are saying, if without in any way disturbing a system, we can predict with certainty, that means with probability equals to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. Means I have some object, some physical, some system. I am not disturbing the system, but I can say something regarding the system, some property deterministically without probability. Then what does that mean? That means this is the property of this system, isn't it? And this is saying this is the physical reality. This is the reality. This is the property of this object. I am saying now you go outside, look into the sky. Of course, you have to use some what is called glass, and you will see sun. Am I correct? Am I disturbing the sun? So this is the physical reality. Sun is there. That's why also this kind of statement probably some of you have heard. Einstein is telling, Isn't it the case if I don't look, moon is still there? চাঁদ আমি দেখছি বলে আছে, না চাঁদ আছে তাই আমি দেখতে পাচ্ছি? কোনটা? সেকেন্ডটা তো। দেখো আবার কিন্তু উল্টোটাও হতে পারে, কিন্তু এটা নিয়ে কিন্তু আইনস্টাইন আর রবীন্দ্রনাথের মধ্যে তর্ক হয়ে মানে কথা হয়েছে। রবীন্দ্রনাথ কি বলছে সেই কবিতার লাইনটা আমি খুব ভুলে যাই, আমারই চেতনা রঙে পান্না হলো সবুজ, না মানে পান্নাটা সবুজ না, আমার চেতনা এটাকে তৈরি করছে। আইনস্টাইন বলছে এটা কি করে আবার হতে পারে? চাঁদ তো চাঁদের মতোই আছে, তুমি বলছো না তুমি আমি তাকাচ্ছি বলে চাঁদ তো এখানে এসছে, এটা আবার হয় নাকি? ওই যে চাঁদ চাঁদের মতোই আছে, ওইটাকে ডিস্টার্ব না করেই আমি ওটা বলে দিতে পারছি, ওইটা হচ্ছে ওর রিয়েলিটি। বুঝতে পারছো? এটাকে বলছে ফিজিক্যাল রিয়েলিটি, বস্তুর নিজস্ব প্রপার্টি। আপেলটা কি? একটা আপেল মানে কি? আপেল মানে কি বলো? ফল। তাহলে আরেকটু বেটার উত্তর দাও। লাল, তার মানে একটা কালার আছে, শুধু কি তাই বলবে? একটা পার্টিকুলার টেস্ট আছে, আমি যদি ধরি একটা পার্টিকুলার তার মানে এই সমস্তগুলো কালেকশনটা আপেল। আচ্ছা এবার আমি করলাম কি, তোমাকে আমি সেন্সেশন তৈরি করলাম ব্রেনে সবগুলো জিনিস, তাহলে তোমার কি মনে হবে আপেল? কোশ্চেন গুলো এই ধরনের কোশ্চেন। তার মানে আপেলটা কি আগে থেকেই ছিল, না আমার এই সমস্ত কনসাসনেসের কালেকশন আপেলটাকে ক্রিয়েট করছে? আইনস্টাইন বলছে না, আপেল তো আপেলের মতোই আছে, ওটা তো রিয়েলিটি ওর। আমাদের কনসাসনেস দিয়ে আমরা ওটাকে এক্সপিরিয়েন্স করছি, সেই জন্য ওটাকে তো প্রিসাইজ করতে হবে ল্যাঙ্গুয়েজটাকে, এটা ফিলিংস ছিল। সেটাকে আইনস্টাইন প্রিসাইজ করছে কি সুন্দরভাবে, দেখো বলছে যদি সিস্টেমকে ডিস্টার্ব না করে আমি তার কোনো প্রপার্টিকে পারফেক্টলি বলে দিতে পারি, তাহলে ভাই তুমি তো এটা মেনে নেবে যে এটা সিস্টেমেরই প্রপার্টি। দেখো এটাতে কিন্তু বোরেরও আর কোনো আপত্তি করার জায়গা নেই, ও এমন ভাবে এটাকে বললো। চট করে বলবো এটাকে মেনে না নিলে তাহলে মুশকিল। আমি সিস্টেমকে ডিস্টার্ব না করে আমি বলে দিচ্ছি এটা ওর প্রপার্টিটা, এটা ওইটা তো সিস্টেমেরই প্রপার্টি, ওইটা আমার মেজারমেন্ট ওইটাকে ক্রিয়েট করেন। ক্লিয়ার? বোঝা গেল? এবার ওরা দেখাবে কোয়ান্টাম মেকানিক্স, এবং এবার এবার কি বলছে কমপ্লিটনেসের মানে, যদি এরকম কোনো ফিজিক্যাল প্রপার্টি থাকে তাহলে সেটাকে তোমার ফিজিক্যাল যে নতুন থিওরি তৈরি করেছো সেটাকে কিন্তু তোমাকে এক্সপ্লেন করতে হবে। দ্যাট ইজ দ্য রিকোয়ারমেন্ট অফ কমপ্লিটনেস। ক্লিয়ার? যদি এরকম কোনো ফিজিক্যাল প্রপার্টি থাকে, তুমি যে নতুন থিওরি তৈরি করেছো অনেক কষ্ট টষ্ট করে, তোমার থিওরি কিন্তু ওটাকে এক্সপ্লেন করতে পারতে হবে। এইটুকু ডিমান্ড তো আমরা করতে পারবো থিওরির কাছে, সেটা হচ্ছে কমপ্লিটনেস। এবার ইপিআর প্যারাডক্স, এটা ইপিআর প্যারাডক্সটা ইপিআর অন্যভাবে বলেছিল, পরে এটাকে সহজ করেন ডেভিড বোম বলে আরেকজন সায়েন্টিস্ট। বোম তোমরা হয়তো পরবর্তীকালে একটা বইও পড়বে, খুব বিখ্যাত বই, দ্য আনডিভাইডেড ইউনিভার্স, দ্যাট ইজ বাই ডেভিড বোম। বোম অ্যান্ড ওনার একজন স্টুডেন্ট হেলি, বোম এবং হেলি। তাই এটা একটা পিকুলিয়ার জিনিস। কি হচ্ছে, একটা সোর্স, সোর্স থেকে দুটো পার্টিকেল বেরোচ্ছে, ঠিক আছে? দুটো পার্টিকেল বেরিয়ে একটা পার্টিকেল তোমার কাছে আসছে, তুমি এখানে বসে আছো, আরেকটা পার্টিকেল তোমার বন্ধুর কাছে পাঠিয়ে দেওয়া হচ্ছে যে আলফা সেন্টুরায় বসে আছে, ঠিক আছে? আচ্ছা এবার এই পার্টিকেলটাকে এইভাবে আমি লিখেছি, কিছু একটা সিম্বল টিম্বল কিছু একটা আছে, যাই হোক ওটাতে ভয় পাওয়ার কিছু নেই, আমি সহজভাবে বলার চেষ্টা করছি। তুমি এখন এই পার্টিকেলটার উপর মেজারমেন্ট করছো, এই মেজারমেন্টটা দুটো আউটকাম হতে পারে, লাল রং বা নীল রং। এখন মেজারমেন্টটা আবার কিরকম করতে পারো, এই জেড ডিরেকশনে করতে পারো, আবার এক্স ডিরেকশনে করতে পারো, এরকম তোমার কাছে অপশন আছে যে তুমি পার্টিকেলটার কাছে গিয়েছো তো এটার উপর জেড ডিরেকশনে একটা মেজারমেন্ট করবে, করে একটা লাল পাবে অথবা নীল আউটকাম পাবে। সেই লাল নীল আউটকামটাকেই আমরা জাস্ট 0 অথবা 1 দিয়ে ডিনোট করছি, ঠিক আছে? এবার এই ডিনোট করাগুলোর কিছু সুবিধা আছে, আমরা যেরকম লাল নীল বলে দিই তো এই বলতে বলতে অনেক এমন হয়ে যাবে, তখন ক্যালকুলেশনটা কঠিন হয়ে যাবে। ডিরাক খুব স্মার্ট ছিল, ও তখন এরকম একটা নোটেশনের আবিষ্কার করলো যেটা দিয়ে খুব সহজ যে করে ফেলা যায়, কিন্তু ফিজিক্সটা একই থাকে, যে মানেটা আমি বলছি এটাই ক্যারি ফরওয়ার্ড হয়। এখন তুমি তোমার পার্টিকেলটার উপর জেড ডিরেকশনে মেজারমেন্ট করে দেখলে ওইটার 0, সঙ্গে সঙ্গে দেখবে কি হবে, ওই পার্টিকেলটা 1। বুঝে গেল? এটা এমন ভাবেই এটাকে তৈরি করা যায় যে তুমি তোমার পার্টিকেলটার উপর জেড ডিরেকশনে মেজার করলে, করে পেলে আপ বা 0, তোমার যে বন্ধু অনেক দূরে বসে আছে সেও যদি জেড ডিরেকশনে মেজারমেন্ট করে পাবে ডাউন। ক্লিয়ার হচ্ছে না? তুমি যদি পাও ডাউন 1, ও পাবে আপ। 0. Peculiar না? দেখো এর মধ্যে কোনো peculiar আছে? কেন নেই মনে হচ্ছে? ঠিকই বলছো, কেন নেই? তোমার বন্ধু কিন্তু অনেক দূরে বসে আছে। Oh, I see. So what I'm trying to say, if you perform a measurement on your first system along Z direction, there are two outcomes. That two outcome I am denoting by 0 and 1. If you perform Z direction and obtain outcome 0, the other particle which is at alpha Centauri with one of your friends, if she performs same Z direction measurement, she will get 1. And vice versa. If you get 1, she will get 0. I'm asking you the question, is it very astonishing? Why not? But to me, apparently it is very astonishing. No, I am here. I am getting outcome and she is far apart. What I am getting, her result is correlated with my outcome. Locality, what we said, no information should travel faster than light. So your apparent feelings is that probably locality there is some problem, contradiction with locality. I'm trying to explain there is nothing problem with locality. Let's forget about all these estimates. We'll play a very simple game. I say there are two boxes. Okay, in one box, these two box, one of the box I have put one shocks, another box I have keep another shocks, and now I give this box to you. What shocks I have given to you, left-handed or right-handed? You don't know. And another box I have given to your friend which is alpha Centauri. Now you open your box. What do you see? Let's say you see your one is left-handed. Immediately, what is your conclusion? So it is a correlation, exactly. Yes. Let's say for our understanding today, 2 is sufficient. If more than 2 will come, the other story will come. But to understand EPR, Einstein problem with quantum mechanics, this is sufficient for us. Okay. Okay. So what I'm trying to say, is it clear? So here no magic, nothing is happening. Like if I give you a box, in this box there is shocks. If you just see it, it is left-handed. Immediately your idea is, okay, the other shocks with my friend, that must be right-handed. That is called correlation. So that is happening. So Alice spin measurement along Z, if her outcome is 0 or up, she's certain that Bob's outcome will be 1. If her outcome is 1 down, she is certain that Bob's outcome will be up. Thus, without disturbing Bob's system, she can predict the value of Z measurement, because she is not disturbing Bob, because Bob is far apart. And any disturbance, if I want to disturb Bob from now, how much time it will take? 4 years. 4 years, at least 4 years it will take, because I have to send some signal, then it will create a disturbance. That signal need not to be a light signal, it could be a gravitational signal also. But okay, according to locality, the disturbance will also cannot propagate faster than light. So instantaneously, I am not disturbing her, but I am predicting her outcome correctly. So that means Z outcome must have a reality, because this is our demand of physical reality. If we can, without disturbing the system, I can predict some property with deterministically, that must have a physical reality. So the Z outcome must have a physical reality. Is this argument clear? Fine. The same thing we can do for X measurement. This time we are performing measurement not along Z direction, rather X direction. So same, this state also can be written in the same form, plus minus, minus plus, where plus minus are the outcome for X direction. For Z direction, we are denoting it by 0 and 1. For plus, we are denoting, for X direction, we are denoting it by plus and minus. So again, if Alice get outcome plus, immediately she knows Bob will get outcome minus. If Alice get minus, immediately she knows Bob will get plus. And again, Alice is not disturbing Bob because Bob is far apart. So that means sigma x that also have a physical reality. So now Einstein demand is both are physical reality. Both should be explained by your theory, because that is your demand. That is the demand. That is our demand to a complete theory, that any physical reality should be explained. But quantum mechanics cannot do that. That's the peculiar. Quantum mechanics say, no, I cannot explain that. Then that's why I say, no, then your theory is not complete. So it is an incomplete theory. So if some theory is incomplete, what should be our next target? To make it a complete theory, to come up with a new theory which is complete in that sense. That's why Einstein is saying, while we have thus shown that the wave function does not provide a complete description of physical reality, we left open the question of whether or not such a description exists. We believe, however, that such a theory is possible. So you see, Newton in his Principia book, he raises a question that how gravity is propagating. Einstein solved this question after 300 years. So now Einstein again shows some problem with quantum mechanics, that it is not a complete theory. Then if it is not a complete theory, let's try to make a complete theory, and they believe such a theory is possible. Okay, I'm coming to Bell, but before that, I'll tell you a story. So Einstein writing this paper in 1935, that okay, quantum mechanics is incomplete. We have to make a complete theory. At that time, people try to, all the scientists working in this area trying to say, oh, how to do it. And then somebody pointed out that John von Neumann in 1932, in his book, he has already given a proof that such a theory is not possible. What question Einstein was asking, von Neumann already gave a mathematical theorem and proves that no, such a theory is not possible. So then the story ends. But actually, von Neumann was wrong. His proof was not correct. And historically, one mathematician, she is a lady mathematician, Grit Harman, in 1930 had tried to point out the mistake in von Neumann argument. But at that time, she was not taken seriously. First of all, von Neumann was so powerful mathematician, and you see, history of science is also not very good also. She is a, first of all, woman mathematician. She was not taken due to her gender, she was not taken seriously. That should not be happen, but it happens. That's why we have to more careful regarding that. You have to careful to your friend, to your friend, that okay, due to that gender, it should not happen that she is not given credit. It has happened historically. Though in 1938, Grit Harman pointed out some mistake in von Neumann proof, nobody taken that much seriously to her. That's why that research was stopped for nearly 3 decades, 30 years. Not only that, also at that time, the Second World War is going on. This was also the reason that people are not discussing this question anymore. But after 30 years, this guy appears, John Stuart Bell. And John Stuart Bell was a physicist from Northern Ireland. And Bell's career began with a UK Atomic Research Energy Establishment. In 1960, he moved to work for European Organization for Nuclear Research, CERN, in Geneva, Switzerland. There he worked almost exclusively on theoretical particle physics and on accelerator design, but found time to pursue a major vocation investigating the foundation of quantum theory. So he was, by practice, was an accelerator designer. But sometimes he was also bothered about this question, that okay, some question was there in 1935 that was not resolved. So in his term, I am a quantum engineer, but on Sunday, I have because I have to do all these things, because otherwise government will not pay me. I have to do. Engineer is not a bad word. Engineering is always, because somebody say Einstein is the greatest mechanical engineer in all time, because he gives the mechanical description how gravity is propagating. Here I am using the engineer in a very praising sense. So I am a quantum engineer, but on Sunday I have principles. Principles means he used to bother about those foundational questions, that, oh, Einstein raises a question, von Neumann give a proof, but some problem was there that has to be resolved. So now in 1964, Bell come up with a very innovative idea, very simple idea, that, okay, who is correct, Einstein or Bohr? That we have to resolve. Okay, how much time I have? At 10-15 minutes? Okay. So let's try to understand Bell idea. Again, very simple. Let's play a game. So game will be again played between two parties. Let's call one Alice and one Bob. So if we say we'll play a game, what comes to your mind? There should be some player. So these are our players. And there should be some referee who will monitor the game. We will also bring referee here. And there should be some rule. Let's say you play football. There are some rule, no, if the ball goes to there, then it score 1. This kind of some rule you design. Here we will also impose some rule. And this game is very simple, thought experiment, thought game. It is not that much complicated like football. So Alice will ask some question. Sometimes she will ask x0, sometimes she will be asked x1. Similarly, Bob will ask some question y0 or y1. But the Alice is here and Bob is at Alpha Centauri. Alice knows what question is given to her. She doesn't know what question is given to Bob. Similarly, Bob knows what question is given to him. Okay? He doesn't know what question is given to Alice. And their answer is only +1 and -1. That's all. So referee will say, okay, Alice, this time question is x0. Alice will say, okay, my answer is +1. Referee will say, Bob, okay, your question is y1. Bob will say, okay, my answer is -1. So is the rule clear? This is the playing rule. Means rule of the, means this way you have to play the game. But another condition is there. No phone will be given between Alice and Bob. What answer Alice is given, that is not known to Bob. There is no phone call allowed. Clear? So denote A and B, the measurement outcome of X and Y, the measurement settings denoted lambda, the hypothetical hidden local variable. Hypothetical hidden local variable means the theory what Einstein is dreaming for. That, okay, there is some complete theory should be there. Let's say that theory is described by something, that hypothetical theory, that we are denoting by some parameter lambda. That such a theory exists. So that is our theory. It has some more mathematical structure, but for our today's purpose, that is not required. Such a theory exists. So now we will play this game many times. So what we will generate? We will generate a probability distribution, conditional probability distribution. That, okay, this means Alice is giving outcome A and Bob is giving outcome B, condition that, provided that Alice is given the question X and Bob is given the question Y and their state is that lambda. So we are playing this game many times and we are calculating this probability. And rule is same, that when the game will be played, no communication will be allowed between them. This is because why no communication will be allowed? Because we want to make our theory compatible with locality condition. That we want to check. That's why this condition is put. So now Bell, here actually it is a one-page calculation. I haven't shown it, not very complicated calculation, but for the time being, you just believe me. This is a just one-page calculation. Bell has shown that the theory what Einstein was dreaming for If such a theory exists, then the joint probability will become factorized. That means Alice, she will answer her question looking into her input. She doesn't know Bob's input. That's why Alice's outcome depends only on her input X. That's all. And the joint, your new theory, what we are dreaming for, that lambda theory. That's all. Similarly, Bob's outcome will be depend on the question given to Bob. That is the locality, local realistic theory, what EPR was dreaming for, that we believe such a theory exists. If such a theory exists, then in this game, the outcome probability should be factorized like that. Then he proved that, okay, these are probabilities. From these probabilities, we can calculate the expectation value. If we know the values and we know the probabilities, we can know the expectation values. These are just nothing. These are just means statistical expectation values. He proves that if this probability is factorized like that, then this expectation value should be bounded by 2. That's all. Only this is the Bell's inequality. Some inequality is coming. That's why you call it Bell's inequality. If a theory satisfies locality or reality condition, what EPR was dreaming for, if that is the case, then in this experiment, sorry, what I have to do? Then this expectation value should be bounded by 2. So again, now this is, I say just one page calculation. But for the time being, forget about the calculation, what we conclude so far. So if such a theory exists, then in this game, this particular value which we can calculate should be bounded by 2. But now if I show that, no, actually in real life, if you play this game, the value become more than 2. What should be your conclusion? That means such a theory is not possible. So now we have a test, we have a way to check whether such a theory is possible or not. Einstein and his colleague, they were believing such a theory is it's possible. But Bohr was asking, no, it is not possible. That was the debate. Now Bell gives us a way that, okay, let's try to play this game. If we see that this success, this particular quantity is bounded by 2, then okay, Einstein is correct. There is a possibility of such a theory. But if it becomes more than 2, it is not possible. Now we have he opens up a way to do this experiment. Now how to do this experiment? We will again here create some photon source, light particle source. One photon will go to Alice, another will go to Bob. These experiments are very difficult experiment because we have to address each of the photon individually. To perform this experiment, we have to address each of the photon, light particle individually. That is very challenging. But at least theoretically now a avenue opens up to us. No, that's called Bell's inequality. And we can show using quantum mechanics, this value can go up to 2√2. So violation of Bell inequality is possible. Again, so far mathematics, theoretical. But now we have to go to lab, we have to perform this experiment. If we, in experiment, if we really got it is violated, then what will be our conclusion? The theory Einstein, they were dreaming for, that is not possible. And these 3 guys, they have performed this experiment. In Nobel Committee listed 7-8 experiments, around 10 experiments, but more than nowadays more than 100 experiments has been performed by different experimental group, and all the experiment tests tells us that yes, we are getting violation of the inequality. So what was you were thinking that Einstein is correct? Unfortunately, Einstein is wrong in this case. So now quantum mechanics is not local. A local realistic theory is not possible for quantum mechanics. It's a non-local theory. Okay, so conclusion. In Bell's theorem, lambda denotes the state of system as described by any possible future physical theory. In this sense, Bell's inequality go way beyond quantum theory. That's why you try to understand the question. I don't build up a theory. Before that, I am telling whether such a theory is possible or not. That's the beauty of Bell's theorem. You don't have the theory. Rather, you are doing experiment and looking into the experimental result, you are trying to discard. No, you should not try that. That is not possible. My experiment is telling that such a theory is not possible. So it is not about quantum mechanics. It is whatever possible theory you are trying to construct regarding nature. Bell's theorem is actually discarding a class of such theory. That's why Bell's inequality go way beyond quantum theory. A violation of Bell inequality proves that no future theory can satisfy the locality condition. Caution. Despite being elegant and simple, Bell inequality is often understood incorrectly. You see, I am actually quoting from Nobel Committee when I was listening their speech. For instance, consider the scientific background provided by the Nobel Committee. A few lines after correctly presenting Bohm's non-local hidden variable model, one reads that Bell inequality violation shows that no hidden variable theory would be able to reproduce all the result of quantum mechanics. This is Nobel Committee is saying. This is completely wrong. Actual statement is no local hidden variable theory is possible. They are saying no hidden variable theory is possible. That is not correct because Bohm already gave a hidden variable theory. That theory is non-local. Actual statement is no local variable theory is able to reproduce all results of quantum mechanics. And few lines further, locality is defined as no signaling. Again, this is some technical issue. No communication without any physical object carrying the information, despite the fact that one of the main contribution of quantum information to the foundation of physics is a clear distinction between these two concepts. Another mistake they have done, Nobel Committee, when they are citing this work. So that should not be case. So you see, you intuitively understand Bell's theorem is we don't have to do lots of mathematics. You see, what mathematics you have to do so far? Just basic concept of probability. Even though it is so simple mathematics, sometimes people misinterpreted the implication of this theory. Even Nobel Committee, they are misinterpreting it. So on the conceptual side, the violation of Bell inequality dramatically revolutionized our worldview. Newton's theory of gravity was non-local. Not only that, even signaling, you can send faster than signal. But Einstein improved on it, making gravity local. It is thus not surprising that he strongly objected to quantum non-locality, not fully appreciating that it is of a very different sort. Newton non-locality and quantum non-locality is different. Newton non-locality you can send faster than signal. In quantum non-locality, okay, something is happening, but that will not allow you to send faster than signal. That is very peculiar. Einstein could not appreciate that at that time because that is very natural. He was actually, you try to think from Einstein perspective. He is solving a question that was open to humankind for 300 years. That give a local description of gravity, and he is successfully give that. So automatically all the thought process will go in that direction. So now, yeah. So now one can ask, okay, yeah, I'll just last slide. How long Bell universe will last? If George Werner Shaw asks this question, it will forever because it is experimentally tested. So in contrast to Newton non-locality, quantum non-locality is here to last forever. The experimental evidence is clear on that point. So, and it has lots of new applications, quantum cryptography, quantum communication, those are aspects of an application of quantum non-locality, but that we cannot discuss today. I'll just end with two remarks, one by John S. Bell. For me, it is so reasonable to assume that the photons in those experiments carry with them programs which have been correlated in advance, telling them how to behave. This is so rational that I think that when Einstein saw that and the others refused to see it, he was a rational man. The other people, although history has justified them, were burying their heads in the sand. So for me, it is a pity that Einstein idea doesn't work. The reasonable thing just doesn't work. Okay, we have to take it. And finally, another quote by David Marmin. What makes the pursuit of science so engrossing is to learn that one's most strongly held belief can be completely wrong. The search to identify and correct the old errors can lead to deep insight into nature. The world would be a far better place for all of us if this joy scientists find in exposing their own misconception were more common in other area of human endeavor. Okay, thanks for your patience. And if you have some question, I can take.
Hello. Thank you so much, sir, for your very, very encouraging and interesting talk. And I think that all the students enjoy. But unfortunately, we are very much lagging behind the time. So if you, I'm unable to take any question in this session. So if you have any time after the lunch session, the student will ask you the question. Okay. I know you are very eager to know so many things from sir, but I'm very sorry about that. Okay. So thank you. So let us give a big hand to our speaker. So we are now starting. Hello. We are now starting the next session. In this session, the second speaker invited talk. The talk will be delivered by Professor Dr. Biplab Sarkar. So say something about Biplab Sarkar. Dr. Sarkar is an accomplished medical physicist with a wealth of experience and expertise in the field. He holds MSc in physics from Calcutta University and diploma in radiological physics from Bhabha Atomic Research Center, Mumbai. With over 10 years of dedicated work as medical physicist, Dr. Sarkar has contributed significantly to various esteemed institutions. He started his career as medical officer at RST Regional Cancer Center in Nagpur. He later joined Amrita Institute of Medical Sciences, Kochi, as an assistant professor in the Department of Medical Physics, imparting knowledge and mentoring aspiring medical physicists. Dr. Sarkar's expertise led him to assume the chief medical physicist at Amri Hospital, and also he is a senior medical physicist in the Fortis Memorial Research Institute, Gurgaon, and he is having his research in the cutting edge research in advancement of the field. Dr. Biplab Sarkar excelled in professional career, but he has also actively involved in academia. He has served as visiting teacher at both Amrita Institute of Medical Sciences, Kochi, and Jadavpur University, Kolkata, sharing his knowledge, expertise with the students. His passion for advancing medical physics is evident from his extensive participation in symposium and conferences. Dr. Sarkar has also been an esteemed member of various scientific committees, including AMPI 2013 Scientific Committee, the American Association of Physicists in Medicine, and Association of Medical Physicists of India. Dr. Sarkar contributed to the field of medical physics, are not only practical but also academic, as evidenced by his significant number of peer-reviewed research publications. His recognition is outstanding work and dedication. Dr. Sarkar has honored with Young Scientist Award in the Association of Medical Physics in India. His contribution to medical physics continue to leave a lasting impact on field, making him a prominent figure and aspiration to the aspiring medical physicists. So I now request Professor Dr. Sarkar to come to the dais and deliver his talk. Thank you, sir. Okay. So your time is half an hour. Okay. No, you can take that time. Yeah. So I'm sorry, I just forgot to mention the title of his talk. The title of his talk is Physics to Medical Physics, My Journey.
Uh, it is a very long introduction. Thank you for the same to madam. And after miss, I didn't bring any presentation to show here. And I was thinking something what can I speak for half an hour to a audience, which is an August audience. I never speak in front of such people in previously any time in last 20 years. Okay. So that was my challenge. And after the mesmerizing talk by sir, I forgot whatever I thought all of. Okay. So now I have to rebuild from the scratch that what I can speak of. So the field I'm working in is called medical physics, which is majority of the people in general also will not understand or will not know about it because it is a very specialized field. And I mean, it is not a common thing. It's not a physics, it's not a chemistry, not a mathematics and all these things. I mean, this is originated from the physics, but it is taken a separate path out of physics, and now it is utilized for the cancer treatment majorly. Okay. Now my journey starts from somewhere in 1896 when Röntgen discovered X-ray. And then it was actually X-ray was the first X-ray. Majority of the people you have heard of X-ray, right? So this is the basic of our whole modality. Okay, the X-ray is the backbone of whole modality. Whatever it is being discovered, the same principle, same technique being used, and that is being utilized for a group of people, group of patients. You must have heard of cancer right now. It is a very common term in society right now because with the advancement of aging people, I mean, in the last 3 decades, the average life expectancy has increased in India is almost 20 years. So this is the aging disease. I mean, it cannot appear immediately. It cannot appear in a younger age. It can appear in the younger age, which is usually genetic, or some genetic disorders. But it is usually a aging disease. With the age, the generation of cancer takes 30 years or 40 years time to accumulate. Okay, so cancer cells have to act, and then oncogenes have to act accordingly, and so forth, and then we get into a cancerous condition, and then treatment and subsequent lot of pain, agony, and other traumas associated with, especially the social trauma. Okay, now I start my journey at before go for scientific scientific conversation. I just let me know. I born in a village in the Howrah district, in some remote village in a Howrah district, and started my schooling in a private in a government school, typical government school, typical backbencher. Never if it is 50% of marks, I will be very happy. My full family will be very happy. They will be celebrating. Okay. And on the contrary, my brother is a extraordinary person. He was always a topper or something like that. So it is always a contradictory in the family and all these things. So we grown up like this, fighting with each other, fighting with the friends, spending majority of the time in the riverbed or swimming or playing or going here and there or cycling or something like that. Means it's not our childhood was a different kind altogether. So I mean, but what they taught us, in the school it was 11 o'clock to 3:30, and then high schools and all these things. They didn't taught us much, but they taught us a lot of mathematics properly actually, and forced us to learn. They didn't let us go. Even so, I mean, those portions, those things helped a lot in the due course of time. We didn't learn much English. I learned English at the age of at class 6, ABCD at class 6. Okay, so that was my journey. So it's. I mean, I can do it. You can also do it. So there we started from that portion. Now, after the schools and all these things, we started a college. I came to Calcutta in Vidyasagar College. We started our graduation and then to masters in from the Presidency University, or which is now Presidency University, or it was under the Calcutta University that by that time. So we have couple of things. I mean, we started from there, and then I tried a lot of avenues in life. I mean, it's not that I straightforward became a medical physics. I mean, I even don't know until I completed my degree from BRC that what is medical physics is. Okay, even when I started doing it, I didn't know that what is this. I mean, what it is used for, or what is its utility, or what is my career opportunity. Okay, I got it the chance, I go through it. I mean, we don't have much option out there, and we don't think of the options also. I mean, I started after presidency, after the graduation, after the masters, I got selected in the TIFR for PhD. I was rejected for PhD 7 times. Okay, so I mean, I can give you the long list, but I mean, it's just time consuming. Just remember, I rejected in 7 times. 7 times means I got it, then I continued in TIFR for 1.5 year, then I have to leave it for whatsoever reason. Okay, so this is the most vulnerable group of people who leaves the PhD. Okay, they are having so much of bad tendencies, and they became depressed and all these things. But somehow I was not that level, because I know that I'm living with consensus, means I'm leaving this PhD with consensus, because I was not liking to do astronomy as my PhD topic. Okay, so see, this is my fault. It is not the fault with the system. I was working in a laboratory which is actually of 12-degree temperature, and then I was not feeling well for months and all these things, severe migraine and all these things. Then I tried to change the lab, then it didn't happen. So I thought that I'll just leave it, because I cannot sit there for 5 years. I'll die. So better leave. Okay. So sleep better than sleepless nights. So somehow when I was in Bombay that time, so I went to BRC for to meet some friends. They told that you want to leave TIFR, so you come down here. And so what? How can I come down? It's not a school that I just walk in here. They have their own entrance examination, this, that, and then interview. You have to be first class throughout your life, which I didn't have. So my question of getting into BRC is out of question. OECS, Orientation School in Engineering and Sciences, which is the basic course for them. I mean, they produce a large number of people, almost 75. Our time it was 75. Now it is nearly 150, which is actually a very course. You can always very good thing. Some of you can opt for it. I mean, look for it. OECS it calls. Okay, well, there are several hundred courses in BRC. You come down, we'll fix you somewhere. Well, what do you mean? Well, yes, you come down, we'll fix you somewhere. Now there was next month there was an interview, and that time I appeared for that interview, which is called as DRP, Diploma in Radiological Physics, and I passed through. Actually, this was my first success in life. I stood first in the whole interview, national interview. It was around 3,000 people. Okay, so why? Because I was trained in TIFR. They asked me only one question: how a MC works, because they were asking the same question for 3 days. And nobody 3-4 days, and nobody could answer. then the head of the RPAD, he asked me that, you are from TIFR. Can you answer me one question? What? How a multi-channel analyzer works? Yes, I know how a multi-channel analyzer works. So I answered that question, and somehow it was I could get it into the course, and then started the things. And until we completed the thing, we didn't know what is it all for. Okay, so this is actually now it is a bit scary. Now, bit scary and frustrating also, because we are not trained in medicine. Okay, we are starting our medicine. See, if you have to train in medicine, see the agony and tolerate the pain of the person or the patient, then it needs a lot of polish. When you need to polish it accordingly. It's not easy. You cannot see a patient tossing in front of you. It's very difficult, and especially the patients which is going to die in due course of time, within 6 months, within 3 months, within 1 year. You see a child, it's the age of 3 years, tossing in pain in front of you. Nobody can do anything. And so this is the frustration. This is the frustration of the whole process or whole thing. But so why you are doing it? Because you don't have anything better than this. Until today, whatever we can provide to these people is, so what is cancer? Cancer is noted. Written note of cancer is found in 530 BC in Greece. Okay, this is a disease which is already known to human society over before Christ's birth, and this is a cancer is the uncontrolled growth of cells in a fashion like a crab. Okay, so this will have the legs. So it is the primary treatment of the cancer was typically surgery, taking off the thing. But usually what happens, that there is the cells. Okay, the cells will be remaining. If there is 4 cells remaining in the system, then the possibility of cancer coming back is 96%. Okay, so it is a very it is a situation. Say, for example, you must have seen that there is a Hollywood actress, which is, her name is Angelina Jolie. Okay, she removed her one of the breast because she is BRCA1 positive. She will 100% get the cancer in due course of time. Okay, guaranteed. So beforehand, she faced an operation to eliminate the risk of cancer. This is possible now. Okay, now, so, but in general, it is not advisable in a society. And I mean, everything is finally end of the day statistical phenomena. In some cases, it is definitive that it will get it into that position, but some cases it might not happen as well. So so this is the origin of cancer. I mean, it will affect more or less 20% of the human society. Okay, and if it is not treated in a proper time, so it will lead to a serious pain. So it's probably, it's like a diabetes. I mean, diabetes diabetes is a continuous process. It will slowly go. Okay, they will control your diabetes. But in cancer, the diabetes means it is a disease which will grow slowly or fast, depending upon the situation. Lot of other factors are there, genetic mutations are there, but it will have an enormous pain. It's very painful, extraordinarily painful, means it's intolerable. Okay, so this is need to be captured, or this is need to be arrested. So we actually, it is a part of the medical system. This is originate from what sir has shown few slide backs, Marie Curie. Okay, sir has told that she is died in cancer. She is a double Nobel laureate. Okay, and then her husband, she is a Nobel laureate, and her elder daughter, okay, elder daughter, Eve and Irene. Irene is the musician, and Eve is the physicist, and her husband is also a physicist. Okay, so this family contributed most in this part of the thing. Like during the Second World War, Madame Curie has constructed lot of X-ray machines to send it to the battlefields. Okay, because so what is the now again coming back to this position that after the discovery of X-ray, it is in 1896, and Röntgen got the first Nobel Prize in physics in 1901. Sorry, any 5 minutes. Okay, so this is the I mean this is Madam says so. So this is the field we are working in, and in presently there will be lot of incorporation of artificial intelligence in medicine, which is actually a part of the whole system. This, for example, I'll just give you 2-3 examples and close the thing. I mean, I just want to say that this is for the medicinal branches, which is pathology, radiology. Where is they have to see a pattern recognition. So there is lot of influence of the artificial intelligence based systems and all these things. Now, why I'm telling this? Because you people will start your further career or further movement of last night, few days back, I was met one person, he's in class 11. He was talking to me about the artificial intelligence and all these things. So I think this is the beginning of the portion. So I mean, beginning of the story. So where you can always come and pick up all these things. Say there is a pattern recognition things like pathology. Now, another 20 years, probably there will not be any necessity of any pathologist, physical pathologist. It will be all machine driven. Okay, any radiologist. So if you take a X-ray or do some CT scan, it will be machine reported. And you will not believe if it is not machine reported. If it is a human reported, probably people will not believe that. Okay. Similarly, the oncology also, it is a requirement of the prognostic models, which is actually oncology or diabetes. Okay, endocrinology. Diabetes is a common term, but the actual term is endocrinology. So there will be a lot of incorporation of the AI-based systems. Okay, and this is your turn. Now, if you want to start with this programming languages or something like that, it will be due course of time, it will be very helpful, and probably it will be easier to find a better avenue than ever actually. Thank you.
Hello. Thank you, sir, for your very, very nice talk and sharing your experience with all of us and our students. So I just want to take 1 or 2 questions if you have any question, because as usual, we are running out of time. Any question? Yeah, yeah.
Sir, I want to ask one question. I think it will be in behalf of the students only. So the term is medical physics. The profession is a medical physicist. So how much medical do we need to know for this? I mean, what is the biological part that we need to know if we want to pursue medical physicist?
I mean, biological part you need not to learn beforehand. I mean, it is during the practice you need to learn. You need to deal with the patients, and their biology and understanding should be known. That's all. Means it is not the hardcore biology.
Okay, so generally students who don't like biology, they are afraid that maybe they will have to learn
Biology has
for
nothing
this.
to do with medicine.
Okay, so that is a clarification.
Medicine is separate. Medicine is a separate branch. It is not a biology. Means it's a PCM or something like that. It's not like that. Medicine is a separate branch, and there is their own implications. Medicine does not contain only doctors. Okay, there are another 70 grades of professionals in medicines. Okay, even I mean a person who is a lab assistant is also a part of medicine. Okay.
Thank you, sir.
Thank
Another one question. I only one more question I can take. Students, do you want to? Yeah.
Good morning, sir. So I would like to ask one question is, how much radiation is safe for a person? Does it depend on the uh, growth of the cancerous tissues and cells, or does it depend on just the amount of time they have been infected through the cancerous cells?
No radiation is safe. Zero. It is like pollution. Okay. But there is some standard limits. For normal person, there is 2 milli kg. I'll tell you the unit, but later on I'll explain the things. 2 millisievert per year. Okay, and for radiation workers, see, there is a difference between the radiation worker as the radiation worker and the normal people. It is not because they are different kind of human being. Like I am a radiation worker. For my limit is 20. Your limit will be 2. Okay, this is because I am monitored. You are not. Okay, so no radiation is safe. I mean, but you are sitting in a closed room. You are already inside the radiation field. Okay, and this is earth crust, especially the cements. Okay, or you are traveling too much in the air. You are getting too much of you are getting a high dose of radiation. If you are consuming banana, it is a potassium, radioactive potassium contains, banana contains radioactive potassium. So we are all inside the radiation. I mean, you cannot avoid that. I mean, there is a lot of sources of radiation which you usually face in day out life. You do a X-ray, you do a CT scan. So community dose is increasing like this. So there is no radiation is safe, but there is a limits to get into the problem.
Okay. So,
Can I ask another question? This is very generous.
so you, I can take only one question, but that's the end. Okay. So there are lots of question is coming out, but unfortunately the time is very short.
Sir, do we have any better system other than chemotherapy for now treatment of cancer?
Yeah, we have there is no, it is a multimodality treatment. I mean, it is chemotherapy, radiotherapy, surgery, or surgery, chemotherapy, operation, chemotherapy plus radiotherapy, and in different combinations. It is not, there is no better or no worse treatment. It is in combination, they will deliver it.
Okay. Thank you then. Thank you, sir, for very experience, sharing your experience. And the students, you can think of career of medical physicist where
Yeah,
you can contribute a lot.
I mean, I'll expect that some of you should come and join the medical physics, but it's not now. I mean, after the graduation and then post graduation, then you can go into it. And I sincerely thanks the university to calling me over here, and all students also, everybody. Thank you very much.
Thank you so much, sir. So give a big hand to sir. Okay. So with this, we come to the end of this session, right?
Thank you, sir. Thank you, ma'am. So as we draw this engaging and enlightening session to a close, I would like to extend our heartfelt appreciation to our esteemed speakers. Their insightful presentation has provided us with a deeper understanding of the realm of physics, and we are truly grateful for their expertise and passion. So here we will have a short break, a tea break. It will be a 15 minutes. We are already running short of time. So please take the break and come back as fast as possible. Hmm? আমি ভেবেছি
হয়ে গেল,
হ্যাঁ
কিন্তু ফেলিসিয়েট করে একটু ব্রেকটা দিতে পারবো।
হ্যাঁ
Hello, can you hear me? Hello.
Hello. Yeah,
So-
I can hear you.
Okay, so we are going to start at 12:30 because there is some delay. I mean,
Okay, I understand. I
okay.
understand.
Dr. Mondal, hope you have already joined, right?
Yes. Am I
Okay.
audible?
Yeah, you are audible.
Recording in progress.
Welcome back, students. So settle down, please. We will be having a felicitation ceremony. So I would like to call upon stage our speaker, Dr. Manik Boni. And I would also like to call upon Dr. Aparajita Bhattacharya to felicitate him. Thank you, sir. Thank you, ma'am. Now I would like to call upon Dr. Biplab Sarkar for felicitation. And I would like to request Dr. Maumita Mukherjee for felicitating our speaker. Now in this session, we have 3 talks, and this session will be chaired by Professor Dr. Maumita Mukherjee, who is the Dean of Research and Innovation, Adamas University, and also Professor of Department of Physics. So may I call upon stage Dr. Mukherjee.
So very good afternoon to all of you. Our second session today will start. This session, the theme is how physics is connected with industry. So back to back 3 speeches will be delivered by 3 people who are basically from physics background, but now they are doing their work in industry. So how physics connects with industry, we will get some glimpse of that. Okay. So first speaker today in this session is Dr. Saurabh Mondal. Sir has already joined, I think, and a very brief note about brief bio note about Dr. Saurabh Mondal, a data scientist employed in Entivo Technologies Private Limited. His expertise is in the field of statistical modeling, mathematical modeling, machine learning, and deep learning algorithm to address various deep technology-related problems. With a PhD in theoretical physics, just note it, Saurabh seamlessly translation from the realm of physics to the dynamic field of data science. So let us, we are very hopeful that we will get some picture how physics is related to data science from Dr. Mondal. So over to Dr. Mondal.
Thank you, ma'am, for your kind introduction. I hope my screen is visible to all of the audience. So The title of my talk is From Hadrons to Patterns, a physicist's quest for data science. So before joining this talk, I was just listening to Dr. Sarkar's beautiful speech. So Dr. Sarkar did not have any slides, but he gave a beautiful speech throughout his time he was on the dais. So although I have slides, but I tried to build these slides as popular as possible, but still some technical terms, some equations will be there. I will try to explain as easily as possible for the students. So yeah, so my journey begins as a physicist almost more than a decade ago. I started working as a physicist. I started working in strong interactions physics, in the domain of strong interactions physics. So these are the plan of my talk. At first, I will give very short lucid introduction about what strong interaction physics is, and a lattice formulations that we use to deal with is to study strong interaction physics through lattice formulations. I will give a very short introduction to that. Then I will slowly transition to data science and what is data science and how it is related to physics, how physicists needs data and all these things. And slowly then I'll go to the machine learning. And then I'll try to show in a couple of slides how this concept of statistical physics is gave rise to one very beautiful machine learning models. And then I will show you some works that recently we were doing in the NTOB technologies. Those are some deep tech solutions and NLP. I believe all of you have heard of natural language processing these days because everyone knows ChatGPT, right? So these are the four fundamental interactions of nature as of now we know. So these are electromagnetic interactions, gravity, weak interaction, and strong interactions. These are the four fundamental interactions of nature. So among these four fundamental interactions, all of you experience those electromagnetic force and gravity in your everyday life. Whatever the phenomena you are seeing in your daily life, like you are observing anything, so you are getting light through your eyes. So that's an electromagnetic interaction. And you observe the gravitational interaction as well. But there are two other interactions. Those are strong and weak interactions. Those are mainly useful in describing subnuclear phenomena, right? So among these, this gravity and electromagnetic interactions have a range like it's infinite range. But the strong and electromagnetic interactions are they have very small rates. That is why they are just bound to explain those phenomena only in the subnuclear domain. Okay, so the weak interactions among them is at the shortest range, which actually explains the phenomena like nuclear beta decay, nuclear interactions kind of interactions. You know, these days, you know, there's a large hadron colliders experiment that is happening, and that helps to understand basic forces of nature. It mostly deals with force, but yes, there are strong interactions part as well. And the strong interactions sorry. Am I audible clearly? Hello.
So is it from your end, I guess?
I don't understand, but
Okay, now it's okay, it seems.
Okay, is it clear now? Is it clear now?
Yes, sir.
Okay, so the strong interactions. The strong interactions it acts in the range of nuclear rate. Okay, and all the basic interactions have some mediating particles. Okay.
No, there are some feedback again. Lit noise.
ইকো নয়েজ সব রকম আছে।
ওনার ওই এন্ডে কিছু ইস্যু হচ্ছে।
Hello.
বলুন এবার।
এবার clear আছে?
এইখানে
No, no, not yet. হয়নি তো এখনো। আবার
Still
আসছে।
echoing?
না
No, some echo and then some feedback. এটাকে বন্ধ করে দিলে যাবে?
না না এটা তো আপনি
ওটা
কথা
আমাদের
বলছেন,
কথাগুলো।
হ্যাঁ তা একবার বলুন।
Still echo হচ্ছে কি?
না ঠিক আছে, ওকে বলুন স্যার।
Okay, so strong interactions that is okay. So all the four interactions have some mediating particles. Except from gravity, it has something on theory that gravitons are there that mediates gravitational interaction, but it is not confirmed. It's not experimentally confirmed. Okay. So for weak interactions, you have and all the mediating particles are bosons. They obey the Bose-Einstein statistics. And for weak interactions, we have W and Z bosons as the mediating particles. And electromagnetic interactions, we have photons. All of us know photons from the Einstein's experiment, great experiment. You know the existence of photons, right? And similarly, for electromagnetic interactions, strong interactions have mediating particles which are known as gluons. So
Saurabh, have you joined from two separate device?
No, only single device.
Okay, sometimes, okay, now you continue, please.
Okay, so the candidate model for strong interactions is quantum chromodynamics. Okay, so this is in the domain of quantum physics, where you know our everyday phenomena we observe mostly are deals with nuclear particles. But whenever you go to the atomic level, subnuclear level, you need different you need quantum physics. The working principle would be quite counterintuitive, but this explains the reason very well. So in strong interactions physics, you know from your school study that the particle that's everything you see are built upon of atom molecules and atoms, and even you know from your physics that these atoms are built with it has nucleus and it has electrons. So nucleus are built with protons and neutrons. Strong interaction physics deals with describe these phenomena. So with the strong interaction physics models that these protons, neutrons, these are actually barriers. These are even built up quarks. So the protons and neutrons are not particles, but they are built up quarks. These protons and neutrons, they are built up of 3 quarks. That's why they are known as baryons. And there are other kind of hadrons. These baryons and mesons are both these are hadrons. So the baryons are made of 3 quarks, and mesons are made of a pair of quark and antiquark. The thing is that the interaction, how these quarks they interact with gluons. To describe their interaction, you need strong interactions. Okay. So one beautiful phenomena of strong interaction physics that I am showing is the quantum law. Let's say you have a meson, that is a pair of quark and antiquark. So the property of strong interaction is that, as we know from the electromagnetic interaction and gravity, the potential of gravitational interactions is inversely proportional to the distance of the, let's say for gravity, but in body, its gravitational potential is inversely proportional to R, where R is the distance between 2 bodies. But in case of strong interaction, this potential actually not inversely proportional, it's directly proportional. Is directly proportional to the distance. Okay. So if you give some amount of energy to your mesons and try to separate these quarks and antiquarks, it won't be able. It is not possible to separate quarks and antiquarks. It's free quarks.
Dr. Mundal.
No, I think even from your side it is equal. It is even equal from your side. Okay. Is it clear now? Hello.
I think some technical glitches are happening. Dr. Mundal, can you hear me properly?
Now I can hear you.
Okay. So in case if there is any problem from your end, what we can do, we can continue with the other speakers. And once
Okay.
we finish, we will back to you. Okay.
Okay.
Okay. Thank you. Thank you for your joining and participation.
Okay.
So our today our second speaker in this session is Mr. Orijit Sinha Rai. Acha, acha. এটা বন্ধ করে দাও দেখেছি কিন্তু ল্যাপটপ তো মিউট করে দিয়েছি So Mr. Sinha Rai is currently working as a senior scientist in TCS Research Kolkata. He has graduated from University of Calcutta in 1996, followed by postgraduate diploma in instrumentation from University of Kolkata in 98. Thereafter, he joined the Portland State University ES and completed a master's in physics and a master's in electrical and computer engineering in 2003. Currently he is co-leading the standoff sensing research area for application in both biomedical and industrial areas through ultrasound sensing, photoacoustic sensing, and microwave-based sensing technique. He has published a good number of research papers in frontline journals and 40 patents grants in his name. So let us welcome Mr. Sinha Rai today for his speech.
Thank you for the introduction. And I'm very pleased to be here. And thank you for giving me the opportunity to talk to the students for the connection to industry with physics. And I'll try my best to give you some glimpse. So let's start. So basically, I will first show you what we are doing in TCS RNI. And then I'll talk about my personal experience of physics and how you can build a career and what is the possibilities there. So this is the line that I always remember. It says all science is either physics or STEM collected by Rutherford. So with that, we start with physics. And in the industrial applications, there are what we are doing in TCS RNI. There are a lot of different groups, but where I work, we do things with acoustic sensing, that is ultrasound-based sensing, photoacoustic sensing, RF sensing, and there is something called computational sensing, but it is more of computational side, so that I won't talk about. So I'll talk about the pure physics-based applications that we'll do. So first, one use case scenario that I want to tell that I don't know, do you know any spirometric test or something like that? If someone has some problem in lungs, they has to go to a hospital and take spirometric test, and which is nothing but it will look for your breathing pattern, mainly the how much volume you're exhaling, inhaling, and then the problem is it is very painful to take. So a patient who cannot even breathe correctly, and she or he needs to actually forcefully breathe and do some maneuver cycles, and that is very painful. So what we wanted to develop is some very simple flow sensing, airflow sensing, directional airflow sensor that will capture your breathing pattern. And with artificial intelligence or pattern recognition, if you can train that, and if you can catch the early detection of this lungs problem. Of course, once there is some red lights from our this kind of screening tool, you have to take a spirometry test. But before that, we can eliminate those tests, or you can actually start treatment even before that. So if you see some red flags. And this is, I'm giving this example because it has mix of both, one physics and one is the machine learning. The physics is here, you know, the time of flight of a signal. When you do the main fundamental, you send us ultrasound, you receive ultrasound, and the speed of sound is dependent on the speed of the medium. And here your medium is where you are blowing, actually you're blowing the air, so the speed changes, and that is the fundamental thing that you sense to capture your breathing speed or breathing pattern. So that was fundamentally how all the spirometer does, or what we have done here developed. We, instead of doing the time of flight of measurement, we did a phase-based measurement, which is much more sensitive and easier to actually implement. In terms of electronics, it is very easier to implement. It is much more sensitive. And you can see the graph where I can see it is someone is actually breathing in and breathing out. And with that pattern, we have now comes to the next part is the machine learning stuff. And then we gathered a lot of people who just smoke. We just wanted to see how we can do it in our lab. So there are smokers, there are non-smokers, and with this kind of simple machine, we can detect the smokers, and we can classify actually who are smokers and who are non-smokers with this kind of simple technique. And so this is nothing but the applied physics. And another thing we do is we do liquid characterization, or you can call it a fluid characterization. So with that, you can see we use acoustic interferometry to actually measure the density, the velocity, and the attenuation of those the ultrasound that we send through the medium. And the basic fundamental is, if you send a ultrasonic pulse and it goes through a medium, it captures the essence of the medium. So with seeing the response of it, you can calculate the velocity of, you calculate the density, you can calculate the viscosity, everything. So where you use it, it is like, for example, if you have a sealed container, say, for example, you have a bottle of Coke, and you want to see if it has degraded or if it is adulterated. So there is no way you can do it without breaking or doing a chemical test, but with sound you can do it. So you just put two sound probes opposite to each other, or it may be same in the same location. And by simply looking at how sound behaves in this thing, you can actually calculate all the parameters of this fluid, and you can actually tell if the fluid is adulterated or something else. So this is one kind of applications that we are doing. And then there are another kind of applications what in TCS RNI we're doing. It is defect detection in a structure. So it can be any structure, wherever we are doing it in a lab. So say there is a metallic sheet and it forms some cavity inside, or something went wrong while manufacturing. You have something inside, and which is you cannot see from the outside. I mean, if you can take a picture of from a camera, but it won't see the inside. You can only see the surface. So there also we use the ultrasounds, and we can figure out not only what kind of defect it is, if it is a crack or if it is a void or if it is something else. Also, you can actually localize it where it is. You can see the lower picture, we can localize it where you can simply send the ultrasound, and you have array of ultrasound, and if you can process that, you can figure out if there is a hidden defect inside. So then comes the photoacoustic sensing. It is mostly the acoustic-based sensing as well, looking at the acoustic parameter. When some acoustic wave travels to some medium, what happens to the acoustics wave. But here you can do it with a non-contact manner. So you can shoot a laser, and the laser will create the acoustics for you. And if you can now record the response of it, you can actually, and this is more sensitive than acoustics. The photoacoustics is more sensitive. And here we are doing some experiments where people are coming and saying they have paint on something, but they don't know what is the thickness of the paint. And you have to do it. How can you actually do it? Right now, they take a sample and they break it, and they have their own measurements. So here with the photoacoustic technique, we can shoot a laser and find out the acoustic pulses and figure out what is the paint thickness, and in a kind of micron level and you can figure out what is the viscosity of something. And the viscosity, there is some oil company that came and they wanted to understand the change in viscosities, because all the machine they use this parameter very carefully. If the viscosity changes unnoticedly, then there will be a problem in the machining. And the problem even increases when there are some what you call anomaly comes, because there will be some soot particles, that is the carbon particles, and say maybe iron filings that is getting mixed, and then you have to detect it. So we have done something in our lab, so we can at least classify in some level that if it is a contaminated or what kind of contamination is in. So is it a water mix, or it is some carbon soot mix, something else. There are another kind of application what we are doing with microwaves, where you have radars, small radars. Nowadays, these are very cheap. And where we wanted to see the health of a machine. So any machine, while they are actually in operation, they vibrate. So the vibration parameter, if you can really figure out, then it also tells something about the machine itself, machine health itself. And again, it's a non-contact, because in a machine, if something is rotating, you cannot just attach an accelerometer there. You have to use some non-contact kind of measurement system. And here a radar comes very handy. The only problem, what we noted, that with a radar, it will pick out it will tell you what are the frequencies, what are the frequencies he is observing. It is observing actually, because it bounces back from the surface, and you get the frequencies, but it cannot tell from which location the frequencies is coming. So this is where we have developed our ideas. So this is where we used a stroboscope as well. Stroboscope is nothing but a high frequency light source. And what happens if something is rotating or vibrating, if the light source frequency and that rotational frequency matches, you will find that the rotation seems like it freezes. I mean, this is a bit frequency it will generate, and you will suddenly find, say, if you are looking at a rotating fan, you'll suddenly find with some tube lights or something, if you illuminate that, you'll find that you can see the blades clearly. It will kind of look like standstill. And with that, if you use this kind of two modalities, one is the RF sensing, one is the stroboscope, you can actually spatially locate the vibrational frequencies, because the radar will give you all the frequencies, say maybe F1 and F2 and F3 is coming from a body. And now if you start strobing on this object with this F1, F2, F3, you will find the portion which has this F1 frequency will freeze. You can see it, and then you use simple camera to capture it, and you can report that this is the location and this is the particular frequencies. And with that, next, so there are a lot of things we are doing with industries, and what I want to actually stress here is that it's all based on the physics. Whenever you are trying to deal with sensing and you want to come out with the new sensing ideas, it has to be with physics. The machine learning will come later, but the physics has to be there. The first thing is the physics. What is the physics of it and how you can actually take advantage of it? And the futuristic sensing that we will start in, we have already started. It is called RF metamaterial and plasmonics. So I'm not going into deep into that, but these are all based on physics. Without physics, you can't do anything on that. So now I will talk about some focus on machine learning as well, because nowadays everywhere you find that people want to learn machine learning. As I already told you, so there are scenarios where you have sensors just like the flow sensors, the airflow sensors of your lungs, and you can just record the pattern, and you can use machine learning to classify things of a bad conditioned lungs versus a good one, or maybe even middle condition, something like that, which is fine. But the fundamental thing that you have to first capture this inflow and outflow, the pattern correctly. If you are wrong there, your all machine learning will be wrong. So all inference will be wrong. So the first focus has to be on the physics of it, and if you are correctly capturing it. Now there are another thing, what I found, that there are a lot of things are coming out with machine health, where they want to actually predict the health of a machine. Just like I have shown you, this is the one way of looking at the vibration and see what kind of vibration is there and what kind of pattern is there. If the machine is going down, then how the pattern changes. The problem with this is with machine learning, as long as you are applying in the sensing modalities, what I found, to get the data. So this is very, very difficult. So for medical, this is fine. You have a lot of data with diseased people. You have there is no problem. But with this kind of machining stuff, I mean, there is a problem with getting the data, because if you want to detect what happens if a machine breaks down, you need a lot of data while the machine has broken to some extent. But who will actually make their machine broken to just give you data? No one will do that. And that is the problem. And only data does not mean anything. You have to have level data. And that is the problem. While if someone wants to only do machine learning, only learn from the data, so that's the problem. So you have to have a mix of that. Yes. Can use them as well. Yes, that you can always use. The new machines are coming with embedded sensors. With these sensors, you can always collect that. But the problem is the sensor will sense. But say if you have a drilling machine, right, and the drill bit is going bad, right, While it is going bad, you need that data. Otherwise, it does not matter.
It's a problem for a hardware, but there are some error codes in software.
Oh, you want to simulate it or
Yes,
something like
yes,
that.
yes.
That can be done, but the main thing is that how good is your simulation? Because in real sense, I'll come to that. For this particular thing, what I was showing as a photoacoustic. So where we wanted to try the photoacoustic signal to classify if there is a contamination of different kinds. The problem was to actually in the lab to produce that much of data, because you need a lot of data, and in the oil, if you want to add some carbon soot particles, these are in very low quantities, 1%. Before that, you have to actually identify. You cannot just put 1 gram and do a mix and do it. Impossible. And so it is very difficult to actually train those data like that. So in that case, what you are saying, what we have done, that we have used a simulator. So there are a lot of physics-based simulator, right? COMSOL and everything. So with that, we actually generated the data for training. So that is another way. But another thing, if your training data is wrong, if every simulation will have a lot of assumptions. You cannot just recreate everything with a simulation. It's not possible. So if your assumptions are primarily correct, then you can generate a lot of data with your machine, with your simulation model, and then train. That is better. Instead of trying to generate the data in the lab, it's impossible. So that is another approach. Okay. And then there is another thing I'd like to stress here. When for the data science, or what you could learn from the data, physics is also learned from the data, right? It's a PV by T constant. So someone has measured P, V, and T, and he has the data. Any measurement is your data, and they learned the relationship. So what is the difference? And your machine learning also learns from the data. What is the difference in that? The difference lies in the fact that in physics, you have a theory, a meaning of it. You know how things are getting generated, how the data is getting generated. How P and V is affecting, and what is the physical significance. For example, if I increase the temperature, you'll find then the particles will have more energy, and it will bang more on the wall, and it will exert more pressure. So these logics, so this is what is the beauty of physics. It explains things to you, how things are getting generated. Now, from a machine learning purpose, if you don't care about the physics, you just give the data. It can also give you some decent result. That's why people are doing so much thing. But the problem is, it is basically solving an optimization problem, whatever you do. And they will use the same optimization problem, and you will optimize, you will get the data, you will optimize, and it will feed a curve, whatever works for you, that is it. But you don't know what is going on, meaning you don't need a meaning of it. For example, when Einstein put forward the special theory of relativity, the equations was already there. The Lorentz equations is already there. The time dilation, the length contraction is already there. But no one could give the meaning to it. That's Einstein gave the meaning to it. And that is the physics. Unless you understand what is going on. So you have to learn from the data. There is no other. Einstein's also learned from the data, right? The C is constant. With respect to any reference frame, it does not affect. It is C is C. The two fundamental observations or assumptions, right? There is the relative velocity, there is no absolute reference frames. And second is all reference frames, the C is C. So these are two fundamental things. And that is why, how? Because Maxwell has already showed with experiment, the velocity of C is unaffected in C, right? So that is you can take it as a data, or Einstein also took a data. But the problem, he gave the meaning to it. But with machine learning, that is the problem. But now how to take advantage of both of that? So my take would be, you use machine learning, always use machine learning on the data. First, make sure your creation of the data is correct. Otherwise, everything will fall. And second, what the feature you are using with them, because machine learning uses some features. Features means nothing. It's just the discriminative factor. What is the discriminative factor? For example, you want to classify dog versus cat, or dog versus say elephant, then your features would be weight. If it is elephant will be huge and they will be small. So you just use weight, just see the weight and you classify. So in any machine learning approach, you want to take out the features which has some physical significance instead of trying to get any features you want. For example, in our lab, I found people are using all kinds of features they came up with, say fifth order, accelerometer to the power 5, fifth. And somehow if you use that, some results are coming good. But I won't take it because it has no meaning. Although it is fitting good with the mathematics, it is working fine. But I'll rather say that you look for the features which has some physical significance to it. Even if it drops the accuracy, it is good for your long run. Otherwise, it is a overfitting. And you will also find in machine learning, they use number of layers. So neural networks and many layers. And you increase the layer, your accuracy will go up, which is equivalent to curve fitting. So if you have few points, X and Y, and you don't know how to fit the curve, you try first with linear, then you increase the degree of polynomial. And the more and more you increase the degree of polynomial, you'll find that it will actually fit good. And it is said that you can fit a complete elephant with higher order polynomial. It will touch every point, but this is completely overfitting. So what will fit? It should come from your physics theory. That will fit, even if it is not fitting that good. So that should you take, right? And in the industry, when I'm in the industry for 20 years and mainly with sensing. So I'm talking about from sensing perspective. Whenever I talk about machine learning or whatever, just say that I'm talking about from sensing perspective. So the Newtonian equations and all those things we have done in our graduate studies. But the moment I started my professional life, I never use equations anymore, Newton's equation anymore. So what I feel that all the sensing labs will use is the waves and oscillations. So it may be sound wave that I was telling, the ultrasound, or it may be the microwave, that is the radar. You can be photoacoustics. Anything you do, you'll find that waves and oscillations plays the main role. So you change the phase, you look at the amplitude, how the wave disperses, and you'll find that wave behaves differently with the wavelength. If for example, a light goes straight with the window, right? There's nothing, no bending. But whenever you have a slit, the double slit experiment, the lambda becomes very small, comparable to, then you find suddenly it is bending. So these are the fundamental things, and it works with all the waves, not only one wave. So you learn the waves and oscillations carefully. For example, when I was talking about a guided wave, where I was talking about in a plane sheet, if there is a problem inside, how do you get that? So there we are using the ultrasound, but it is called a guided wave. It's speciality there, where because here when I'm talking, the space is too big and my wavelength is not that small, so it will simply go through. But in a thin sheet, what happens, if your dimension of this the thickness, if it is comparable to the wavelength of the excitation frequency, the sound wave behaves completely different. It will have dispersion, it will have all kinds of different things will come out. So you have to clearly understand those waves and oscillations. Also, we take advantage of resonance and those kind of stuff. And so 2 more minutes. So, and I will encourage you to learn FFT, the Fourier transform and modulation. That will actually come handy. Linear algebra, optimization, and measurement techniques. And in measurement techniques, if you understand how a network analyzer work, you are done actually. And lastly, this is the last slide. Lastly, my experience. So I graduated from US, and there my experience is, this is a typical computer science and engineering class. And you'll find it is crowded. And it is mostly Chinese or Indian. If you go sit, you will find you are in India or you are in China. I mean, it is the feeling. But if you go to the physics department, the crowd is not like that. You have a lot of grants there, a lot of scholarships there, and you will find more Germans are there. So this is one thing you should explore if you want to go outside. With physics, you have this advantage. Do not just jump and go into the engineering. So you will have a lot of things there. So that is it. And any question from the student, I'd love to take.
One or two quick questions? If no, okay, then we can discuss later as well. Today our this is the, before lunch is the third speech and the concluding speech for this session by Dr. Tanusham Chattopadhyay. So Dr. Chattopadhyay is currently working as AGM of AI Labs in Adani Enterprise Limited. He graduated from Vishwabharati University and postgraduated from IIST Shibpur and did his PhD from Jadavpur University as a part of his research work done at ISI Kolkata in 2012. He has published more than 70 research papers in frontline journals and 75 patents got granted across the globe to his credit. So let us welcome Dr. Chattopadhyay today for his speech.
Thank you, organizers, for inviting me. But I have a serious allegations against you, not regarding my travel, not anything. Problem is that just penultimate session of my one with from Arijit, with whom I worked for nearly 18 years. And you have done one serious problem for me. You know that in our lunch table, whatever debates we used to have, you have taken it into the open platform. So everything what was hushed up in the TCS lunch table is now in open platform of Adamas. Let's see. Whatever he told, mostly I contradicted during that lunch table. Again, let me start again in front of you. So it's a nice occasion for you to attend this. He completed that try to stay back in physics before jumping into engineering. And my motivation would be try to come out of physics. So why? I'm from very beginning, I started to read physics in Vishwabharati. So I found that I got very good marks. And I secured some rank in the university also. But unfortunately, I realized that I don't understand the subject. Possibly, both sides of it, every one of you have have something in your mind. Either you understand but don't get marks. Otherwise, you are getting marks, but you don't understand the subject. So this is the time when comes one try to seek for new jobs. So this is the report of last Sunday, according to some job portals, that what are the major skill sets? Let's see. Oh, it's though screen is very big, but possibly you cannot find the topmost one, the what is x-axis and y-axis. Being a physics graduate, I definitely start presenting everything in terms of axis. What is x-axis and what is y-axis? X-axis, I'll come to later. First, let me tell what is y-axis. Y-axis below, that where less amount of job is there. And as you go up, like any axis, more jobs. So you can see topmost is the applied AI, applied artificial intelligence. And bottom one is the quantum. So who are thinking that graduating from physics ensures me at least in this job of quantum, but scarcity of job is there. On the other hand, x-axis gives you the indication of demand of resources. So you see there is a line in the right part. If it is even right, more right, you go more right, less, scarcity of job is less, means more resources available than the demand. So if you see the topmost where highest amount of job is available and highest scarcity or less amount of resources available is nothing but data science. So now you are in a dilemma, whom to believe, TCS or Arijit or Adani, ex-TCS or Tanusham, presently Adani. Let me listen something from the Google people now.
I actually interviewed at Google twice. The first time I failed utterly, and the second time I got through. So there's many paths into interviewing at Google.
Hi, I'm Molly from Springboard, and I'm here with Michael, a data scientist at Google. Michael, thanks so much for being here.
Thanks for having me.
You started off with a PhD in physics, and now you're a data scientist. How did that transition happen?
Yeah, so I think in physics, one of the things that attracted me most to the field that I studied, which was particle physics, was sort of the ability to leverage computer science, mathematical modeling, and data visualization to sort of solve big questions. And the longer I was in that field, the more I realized that that process of kind of problem solving with those techniques and tools, I actually enjoyed that more than the physics itself. So it was a natural transition for me to sort of move to a career that felt like it had higher impact, a wide variety of work, and good career opportunity. And data science was that move for me.
Before Google, you worked at Mercedes.
I
What were
can
some of the
skip
projects
from
that you-
now. So what is data science? You can see that people are coming to Google for data science role from after completing PhD in physics. So there is no airtight compartments are there, physics, engineering, even in Google. So you know that what may happen for other, organizations, because Google is now, is undoubtedly one of the topmost organization in the world in the field of research. So what is the definition of data science? Let me explain it to you first. From disciplinary perspective, data science is a new interdisciplinary field that synthesizes and builds on statistics, informatics, computing, communication, management, sociology, whatnot, isn't? To study data and its environment, including domains and other contextual aspects such as organization and social aspects, in order to transform data to insights and decisions by following a data knowledge to wisdom, thinking, and methodology. Right now, in your lab, you are doing some experiment. Say you are doing, I know that in graduation school, possibly still now craters pendulums are there in the very first years, or so what you are doing there, or some black body radiation T to the power 4. So for these experiments, what you do first, you collect data, then you analyze them, you plot them, and finally you go to your professors. Instead, in industry, I collect data, I analyze them, I plot them, and I go to my customers to show them this is the business. So show them, that's how you can take your business further. Being a physicist, first 3 steps was very common for me. Only change I made that some here interdisciplinary aspect and some organizational understanding. So I know my situation is like that bowler of West Indies who bowled the 23rd over yesterday, because India was 114 already done and still 1 over he has to bat. So I am like that, standing between you and your lunch. So my situation is like that. So instead of big, slides and big text, let me make it a formulation. Okay. So data science is equal to see statistics, informatics, computing, communication, sociology, management, blah, blah, blah. All these things. What it works, that is something very important. So what are the 4 things you need to do? First, what happened based on historical data, and what is the insight there? Modeling, and how and why did it happen? Arijit was talking about some machine health inspection. Historically, machine failed. Why it failed? Can I see it by plotting the graphs? I'll not give you any answer. I'll just throw some questions to you and request you to find the answers in your future. Second, what is happening? You see, whenever I'm telling that what is happening, what are the key driving factors we need to identify to get the insight? That can help for risk management. Next, prediction and forecasting. Very simple thing from possibly first year you heard about, or even for the school days, mean square estimation, some drawing some line, then y is equal to mx plus c, isn't? Even for the pendulums practical, L square, L by T square graph. So there also you are doing some least square estimation and drawing graphs. Same thing. And last one, what best action to take means how can I happen it or how can I avoid it? So these are the 8 bubbles which is important in business perspective. First one, reporting. Second one, statistical analysis. Then alerting. Something is going to happen. Next, forecasting. Means this is going to happen in another 5 minutes or another 5 days. Then prediction. Let me go to the next slide. It is better. So you can see, first thing is the hindsight, where we try to identify what happened. Next, why did it happen? In diagnostics, whatever previous speaker told, that explainability comes here, why it happened. Now we need to understand what will happen. And the last one, how can we make it happen? Means I can give you a real example of the problems, whatever we are solving now. So think of a industry who are producing something like cement or tobacco. The ambient temperature is something you cannot make change it. Means humidity or that temperature is something you don't have any control, but there are certain set points are there. If humidity is like that, if I change it to by switch on some dehumidifier, or if my temperature is very high, if I switch on some air conditioner, it can be done. So first of all, you need to understand what is in your hand and what you can do. And based on that, you have to control the environment, what is not in your hand. So you can see from here, hindsight to insight, data science helps you to go foresight. So definitely question may happen. There are lots of jobs and you are telling that data science is happening. So how to become a data scientist? I don't know whoever has, carefully listened my profile. Most of the time, whenever I am in also audience, I ignore these words. Even, mostly sitting in the last bench, I also ignored the presentations also many times during my student days. So, but unfortunately, I'm here on the other side of the table now. So you see, first one is that you need to understand domain and business knowledge. What is the domain for you physicists? I want to listen from you. What is your domain? Which subject you know best? Physics. Now, we used to say that we have to complete 1.5 honors during our days, because half part of the mathematics honors we used to study as mathematical methods. Possibly the same thing is going on still now. Isn't so? You have to learn a lot of mathematical methods, be it Fourier, be it Laplacian transformations, be it anything. Are you still studying this? Mathematics? You are learning also coding. So you are no more a physicist, you become the intersection of all, means you already become data scientist. So data scientists, that's why I was asking, I studied in physics honors, then I studied computer applications, and finally did my PhD from Indian Statistical Institute. So I prefer to say that if you follow my career path, you can find what is the data scientist. So physics, core knowledge here, then computer applications for coding, and mathematics statistics from ISI. So that's why I can say that I am data scientist. Now it's time for you to go and grab it. Can anyone tell what is this image? Famous painting. Where can you find it? Sistine Chapel, right? What is the name of it? Creation of Adam. So from physics, if you already started, it's fine. Otherwise, you can now think of start to learn some computer and coding and mathematics too. This one is a physicist, and after touching, this is my painting, not Michelangelo's, creation of a data scientist. Thank you. Any question, please? Any question?
Good morning, sir. My question is, nowadays many colleges are coming up with diploma courses, undergraduate courses in data sciences. Do you approve of it? Like being a physics teacher, my first motivation for any student would be to go ahead with basic sciences. Before becoming a data scientist, at least graduate in physics. But nowadays there is a huge shift. They are coming and telling, ma'am, but there is a data science option available right after 12. Why should not I go ahead and grab it? So do you think that physics or these graduates, will it become redundant, or will these people, the ones who are doing an undergraduate in data science and proceeding ahead, whether they will be in a front foot or these people will be in the back foot, or it's just a mind game? That's it.
So it all comes from the concept of, I can say, economics, demand and supply. That's why I started with the slide on demand and supply. So if you see that x-axis of it is the demand supply, right now there is a scarcity of data scientists. That's why, but at the same time, there is no way called shortcut. So who are going to data scientists, they may get the job, but in the long run, whether they can survive at all or not, I also have a big question. But I don't know why you are always creating problem for me. Most of the universities, this syllabus of data science is prepared by me in West Bengal. So how can I say that it is redundant? I have to politically answer it. But my recommendation, I can say that follow my career path, not what I created, means start with basic science, be it maths, be it physics. But like I can say that English, Bengali can never be treated as a subject, they are language. Similarly, mathematics is the language of science. And computer science or the coding is the another language of expression mathematics into computer. So what is the subject they are learning unless and until they are studying physics or chemistry? I'm not telling only physics. I'm talking about basic science. Everyone is seeing the benefit, IoT, analytics, all these things we are talking about. But how can we capture the data unless and until material science is matured? Unless and until my battery is going to dry down, unless and until some research happening in the superconductor or something, it is not possible to do any research. These are just the shortcuts. In the long run, it cannot survive, but definitely because of the present scenario, scarcity of the resources and high salaries, definitely I cannot ignore it. People are taking this path.
Sir, the second part of it, a lot of data science also involves analyzing a particular result. Now, I'm not that aware of this field or the way this field is progressing ahead. Do you think the analyzing part might be taken over by AI or might be very predictable and these people again may lack somewhere?
Here comes an important factor that if you see the recent, 3 sectors for this data-driven approaches, 3 conferences are the pioneer now. One is KDD, knowledge-driven discovery. One is ICML, International Conference on Machine Learning. Another is the Neural Information Processing System, NIPS. Everywhere nowadays, one track is dedicated on XAI, XAI, explainable AI. Now, the question with the recent trend, means recent big hype, is the chat GPT. Everyone is using it. So the basic questions, what any class 12 standard student can answer, that can be answered by chat GPT. But graduates are there, physics graduates are there, where AI cannot answer. XAI is mostly tried. I have seen one statistics today morning only, where it says that 60% to 70% satisfaction level is there. From ChatGPT is output. Who will give this 30%? Who is basic science graduates? But for that, if they keep themselves like this taboo of that, I will not learn engineering, I'll not go for computer science, I'll not learn coding, it will be a problem for them. They need to adapt. Again, a bit philosophical. Being Indian, I have to say that there is, I mean, I'm belonging to that religion where no Sanskrit word for exclusion is there, only inclusion. So I have to, being philosophical, I have to answer that you have to be inclusive in mind.
Thank you, Dr. Chakravarti, for your speech, and definitely I hope the students have gathered knowledge how physics is related to data science, and as he has rightly said, there is no strict barrier between subjects nowadays. So we have to go to the first speech again because we are facing trouble to hear Dr. Saurabh Mondal. So let's try once.
Okay, am I audible clearly now? Hello. Am I audible now?
Oh, acha.
Am I audible now?
Yes, sir.
Okay. I'm sharing my screen.
Bolun apni.
Dr. Mondal, can you hear me properly?
Yes, I can hear you.
Bolun. Yes.
Okay. So where I was there, so is it clearly audible now? Is it clearly audible now?
এখানে বলুন এইখানে
আচ্ছা এইখানে Dr. Mondal, can you hear me properly?
I can hear you.
আমি তো শুনতে পাচ্ছি না কিছু।
তো শেয়ার করাই রয়েছে।
Okay,
এখানে দেখুন কেউ কথা বললে দেখুন
হ্যাঁ আমাদেরটা তো ঠিক আছে, ওনার দিক থেকে ওটা আসছে না, তাই না?
Can you hear me?
এখানে একটা গন্ডগোল হতে পারে, এই ল্যাপটপের আওয়াজটা বন্ধ মিউট করা আছে।
আচ্ছা আচ্ছা
হ্যাঁ এবার শোনা যাবে।
Okay, can you hear me?
এবার ঠিক আছে।
হ্যাঁ ঠিক আছে বলতে বলুন।
So welcome Dr. Mondal. Since we are running short of time, it's my request to you that if you can conclude within 5 to 7 minutes, it will be very helpful for the organizers.
Okay, thank you. Okay, so before that, the technical problem, I was explaining the quark confinement problem. So the fundamental problems in nature is that quarks cannot be found, free quarks cannot be found. This phenomena, to explain this kind of phenomena, so standard perturbative quantum mechanics or quantum field theory fails. So one needs alternative non-perturbative techniques. That is called one such perturbative techniques is lattice formulations, where we use four-dimensional hypercubic lattice, where the quarks or the fermions are placed in the lattice sites, and the gluons are placed in the links joining the lattice sites. So through which the interaction between quarks through the gluons can be simulated. So in means of simulation, one thing you need to explain is that the fundamental concept of probability. So let's say you have a random variable. So to calculate the mean or the expectation value of the random variables, you need to integrate that variable through its probability distributions. So that's how you get the expectation value of any variable. So we do the same things on lattice to calculate any physical observable that is relevant to the strong interaction physics. Let it be observable for any baryons or any mesons. It can be glow balls. Glow balls are glow balls are particle that is entirely made of gluons. So the problem is that in lattice, when you try to calculate this kind of integral on lattice, you'll need a very large number of integration you need to do, and which is not feasible, which is not practically feasible. So one thing we do Monte Carlo simulations. We approximate that expectation value, that is the integration with sum. That is how my screen is showing, where these xn's are generated with the probability distribution. That probability, it was in the definition of our previous expectation value. So you generate the configuration. Okay. Am I audible now? Okay. So with this expectation value, we can calculate any physical observables. Okay. Now we come to the data science. In physics, you deal with, let's say in experimental physics, you deal with a lot of data, and you need to get the understand the physics from the data. So there are and even
You're audible.
okay.
Please continue.
Yes, yes. So data science, what we do, we deal with data science is an interdisciplinary academic field that uses statistics, scientific computing, scientific methods, processes, and algorithms. And during the course of learning physics, even during my the days in masters, we need to understand the numerical simulations and numerical algorithms. And even not only the experimental physics, even in theoretical physics, where you need simulations, you will get a lot of the data, the simulated data that I have shown in the lattice. You will get a gauge configuration. So there will be large number of configuration upon which you need to calculate different kind of physical observables. So that way we just introduced to the world of data. And after doing my PhD and theoretical research, so I just wanted to explore my expertise to use in the real life scenario. So that is why I just translated my career to data science. Okay, so in data science, there you need machine learning, but machine learning is not all of the data science. There are many other things. As one of our previous talks, the speaker was saying correctly that even in machine learning, the fundamental problem is optimization. Even without machine learning, there in the industry, there are a lot of industrial problems where you need to optimize different problems. Okay, so one thing I just want to explain is the neural networks, which is kind of one machine learning algorithm. Neural networks can have many multiple number of architectures through which you can understand the data and you can get the insight of the data. Okay, so in neural network, you generally have it just simulates your physical biological neurons. So where these each of these circles represents one neurons. Okay, and there are in neural network you will have multiple layers. The first layer that is showing in the diagram is called as input layer, and the last layer it is showing the output layers. So through the input layer you put the data, and you can whatever you get the output from the output layers. Now you have in machine learning problems in data, sometimes there are two kind of machine learning problems. That is Yes, sir. So you get the data, and you calculate some output, and from output and your input, you can optimize your objective functions through which you learn the parameters. Okay. Now the diagram bottom, it explains the neural network very clearly. It is it explains each of these neurons that is shown in the top figure. Okay, so let's say you have like 4 inputs and you have 1 neurons. So you are passing 4 inputs through a neurons, and there will be some activation function that will activate whether information from an input will trigger a neuron or not. So that is how the neural network works. Now I want to just show a similarity between statistical physics and neural network. To show that, I will show a restricted Boltzmann machine. This is a kind of another neural network. But this is a two-layer network where V represents the visible variable and where H is the hidden variable. So using this kind of neural networks, what we learn is suppose you have a data. So we want to learn the probability distribution of that data and want to replicate the data that follows same probability distributions. So for that purpose, restricted Boltzmann machines are used, where V are the visible variable where you put your data, and you generate the hidden variable using the Boltzmann statistics that is showing here in this slide. That is probability of you generate given a set of your visible layer, given a set of visible layer data, you will generate the hidden layer data such that the probability of combined probability of visible layer and hidden layer variable is described by a Boltzmann statistics. So that's the thing. And this algorithm actually inspired from the physics. In statistical physics, there are many phenomena that could be described using, for example, magnetism can be described using Ising model. So this model actually replicates the Ising model. So that's the description of this algorithm. I'm not going to the details, and just wanted to show the similar how the machine learning algorithm can got inspired. Okay. Okay. So at NPRV Technologies, what we are doing, we are basically doing 2 kind of works. One is the deep tech solution we're trying to give, but deep tech refers a category of advanced and cutting edge technologies that are based on scientific breakthroughs and engineering innovations, where actually we need scientific foundation, scientific research in many fields, not only physics. That is, you need research in physics, chemistry, biology, mathematics, computer science, and even engineering solutions. So where we actually, what we are doing combining machine learning and artificial intelligence with actual engineering problems to solve these things. Specifically, we are just trying to solve, mostly working in positioning, navigation, and tracking systems, where let's say you have an environment where you don't have GPS. Just we use our techniques to navigate in that situations and tracking these things. You need machine learning and artificial intelligence to solve these kind of problems. And the other kind of problem we are working is natural language processing. You know, the natural language processing is now known to every one of you. Just everyone knows ChatGPT. It deals with, it's a most advanced kind of natural language processing algorithm. So what natural language processing does, you have it just makes the algorithm such a way that machine can understand human language. Okay, so it does in it first. You have a piece of paragraph. Okay, it first tokenize each of the words, and from it trains the algorithm trains that. Okay, so the algorithm trains on the textual data. From the sequential appearance of each words. Okay, from that, each words will have a mathematical representation, that is a vector. Now, from vector in physics, you know 2 vectors are closer when their dot product is larger. Using that similar concept, we can build a vector space that represents the text. And using that, the machines can understand the human language. So the most advanced kind of this machine natural language algorithm is nowadays is ChatGPT, which is basically a generative pre-trained transformers models. We are right now using those generative pre-trained transformers model to process documents, various documents. It can be a legal document or medical document or whatever. So we just process, we use pre-trained transformers model in our natural language processing engine, so that it gets if you input the documents, and if you, let's say you have a document and you want to know what is in document, you have multiple questions from that document. If you put those questions, the natural NLP engine will provide the answers from the document, and it works surprisingly well. So these things we are working. Even we are working more problems like transportation problem, where the network structures, space-time network structures are used. And even we can found similarities and insights from physics in these kind of problems as well.
Mondal. Okay, thank you. So just in conclusion.
I'm just trying to conclude soon. So in conclusion, my journey from being a physicist to becoming a data scientist has been an incredible adventure. The thing is that even the data science, most of the people will tell you that it is a job of physicist or a statistician's job. But the thing is that data science is a multidisciplinary field. The insights from many, many fields are important in this field, even from physics. Not only the input from physics helps the machine learning or data science things, even it's opposite as well. Even nowadays, in many physics problem, the machine learning and artificial intelligence helps the physics problems, to solve many physics problems. So that's this synergy between the two domains that enabled me to bridge the gap between theoretical knowledge and practical applications. It's all about two. Thank you.
Thank you. There may be some question from student, but since we are running short of time, I will request a student to please contact the speaker if you have some question to discuss with him. Okay. So with this, we are concluding second session. Now it's a time for felicitation. So I'll request Shatarupa to please announce. Dr. Mondal, thank you for your speech today. Although it was a technical glitches were there, but we are very happy to get some information from you. Thank you.
Thank you. Thank you for giving me this opportunity.
Thank you.
Thank you so much for the wonderful session. So I would like to request Dr. Arijit Sinha Roy and Dr. Tanusham Chattopadhyay to come up to the stage for felicitation. And I would also like to request Professor Bimal Kumar Sarkar and Professor Aparajita Bhattacharya to felicitate them. Thank you so much. So it's time for lunch. It is the same venue as yesterday. So, but the time we are, as you can understand, we are running short of time. So please come back by 2:30 positively. So by 2:30 we will start the session. So gather here before that, 5 minutes before 2:30. So I'm expecting all of you to be here around 2:25. Thank you. Yes.
Okay, so let's start. So, good afternoon, everyone. Hope you all had a nice time during these last 2 days. So welcome to this last, but definitely not the least, rather the most exciting part of this 2-day-long session, which is the panel discussion on international mega physics projects, where India is playing a very active and integral role, a very pivotal role. And I am Dr. Momita Dev, Head Department of Physics, and for this session, I'll be moderating. So, as you know, you will see that today we have the privilege of being joined by esteemed experts and scientists from our own country, but they are playing pivotal role in all those international mega physics projects. And every time I'm saying mega physics projects, so what exactly are those projects that I'm talking about? I'm talking about the projects you can see on screen. One is the Relativistic Heavy Ion Collider Project at Brookhaven National Lab, USA, RHIC. The second is the Large Hadron Collider, LHC, at CERN, Geneva, Switzerland. And the GSI Facility for Antiproton and Ion Research, FAIR. And last, in our own country, the Indian Neutrino Observatory Project, INO. So the primary goal of this, what is the goal of this panel discussion? Why are we planning it? So the primary object is basically twofold. Firstly, and most obviously, to understand the cutting edge research and the application in the field of physics that these mega projects have contributed to. And secondly, and from our perspective, I think this is more importantly to inspire you. Our aim is to inspire and encourage to all of you because you, all the students, we are addressing basically all the students because you are standing at the conjuncture of choosing your career paths. So you can think, you can take or consider physics as a subject of study at undergraduate or postgraduate level, whatever, because physics is often called a fundamental science, that it forms the bedrock of understanding of our universe, but at the same time, it drives innovation. And during this last 2 days, you might have heard that from medical physics, apart from academics, apart from research, even in industry application, today you have heard apart from academics, that medical physics, finance, there are various sectors where it has application, where there are career prospects. So that's why it is important. And now we will start this panel discussion. So throughout the discussion, our plan is to know a very basic overview of these projects. And then we will try to hear from the experts about the challenges they face, the need for the international collaboration, because 3 of them are international projects. And apart from that, their contribution to society beyond the realm of research, if there is any. So now, so the point is, whether you have a passion for astrophysics or cosmic blocks of matter or the condensed matter physics, or discovering the practical applications of physics in daily life. So whatever it fields in which you are interested in, ultimately, I think this panel discussion is going to be very insightful for all of you. And I know that I have requests from some schools that you have some time limitation, you will have to go. But my request is keep an open mind, try to listen, try to learn as much as possible, because it's not every day that you get to hear from such experts. And ultimately, it's your interaction that's going to make this panel discussion a success. So without any further ado, let's start this program. And for that, I would like to introduce to all our esteemed speakers one by one. And first, our first panelist is Professor Shivaji Raha. Sir, if possible, you can join us on the dais. Thank you, sir. Professor Shivaji Raha, a renowned theoretical physicist specializing in high energy and nuclear physics, astrophysics, astroparticle physics, cosmology, as well as a multitude of areas relating to the global change scenario. He had his early education in the city, culminating in a Bachelor of Science degree in physics from Presidency College. He had his postgraduate training in physics in the USA, obtaining a doctorate from the University of Texas at Austin. He did his PhD under the supervision of John A. Wheeler, who is best known for popularizing the term black hole. After several years of research and teaching in Germany and France, he returned to India to join the faculty of Shah Institute of Nuclear Physics in Kolkata in 1985, whence he moved to Bosch Institute in 1981, where he had been since. He served as the director of Bosch Institute during 2006 to 2016, and also the officiating director of SN Bosch National Center for Basic Sciences, Kolkata during 2014 to 2016. Over the years, he has also held numerous concurrent visiting professorships at a number of leading universities and research laboratories all over the world, including USA, France, Germany, Japan, Italy, Brazil, and other countries. After retiring from active service as a senior professor in 2018, he continues to be associated with Bosch Institute as a researcher. He created the National Center for Astroparticle Physics and Space Science at Darjeeling campus of Bosch Institute, which has attained an enviable international status and reputation within a very short time. He was the chairman of the Joint Scientific Council of the International Facility for Antiproton and Ion Research, FAIR, that I talked about, and the German Helmholtz Institute of Heavy Ion Research, GSI, in Germany. He has authored over 300 scientific papers in leading international journals, authored or edited 8 books, and also written extensively in non-technical publications on various issues. His exposure to science education, teaching, and research in many countries across the globe has instilled in him an abiding interest in the history of science and society. So thank you very much, sir, for joining us. Give a round of applause. Thank you. And now I'd like to request our Pro Vice Chancellor, Professor Dipankar Bhattacharya, to please come on the stage and felicitate Professor Raha. Now I'd like to request Professor Shunanda Banerjee to join us on stage. Please give him a round of applause. And let me introduce Professor Banerjee. Professor Shunanda Banerjee is a distinguished physicist with an illustrious academic journey with an impressive career in high energy physics. His passion for unraveling the mysteries of the universe has led him to hold numerous prestigious appointments and engage in significant research activities. Dr. Banerjee completed his BSc in Physics from Presidency College, Calcutta. He pursued further studies at Imperial College, London. He obtained his PhD degree in high energy physics in the same year, making noteworthy contributions to the field of particle physics from University of London. Throughout his career, Professor Banerjee has held several remarkable professional appointments showcasing his expertise and commitment to scientific exploration. Currently, he is associated with the Indian Association for the Cultivation of Science, Kolkata, ISCS, as an INSA senior scientist since March 2022. Additionally, he serves as a guest visiting professor at the University of Wisconsin since August 2021. His academic journey includes prestigious roles such as guest scientist at Fermi National Accelerator and professor at Shah Institute of Nuclear Physics. Dr. Banerjee has also been an application scientist at Fermi National Accelerator and a senior professor at Tata Institute of Fundamental Research, TIFR, Mumbai. His research affiliations are globally diverse and impressive. He has been associated with CERN in Geneva, Switzerland during various periods. Throughout his career, Professor Banerjee has made significant contributions to various experiments and collaborations. Notably, he has been a valuable member of the CMS experiment at CERN since 1994, and he led the TIFR group in the Bell experiment at the KEK-B asymmetric electron-positron collider from 2002 to 2006. His work also extends to the crystal clear collaboration during 1992 to 1996. The L3 experiment at LEP CERN from 83 to 2004, and at the WA83 experiment at the Omega spectrometer at CERN. So thank you very much, sir. Thank you for joining us. And now I'd like to request Pravisi sir to please felicitate Professor Banerjee. Now, I'd like to request Professor Nabokumar Mondal to please join us on stage. Professor Nabokumar Mondal is an internationally acclaimed physicist from India who, over the past 40 years, have contributed immensely to the development of scientific knowledge in the field of particle physics. He was project director of the India-based Neutrino Observatory INO and was a senior professor at Tata Institute of Fundamental Research, TIFR Mumbai, till March 2016. Currently, he is INSA senior scientist at SNP Kolkata. Professor Mondal's distinguished scientific career has been marked by numerous felicitations and awards. He is a fellow of all the 3 scientific academies of India, Indian National Science Academy, Indian Academy of Sciences, and National Academy of Sciences, and is a J.C. Bose Fellow, and is also a fellow of the World Academy of Sciences for the Advancement of Science in Developing Countries. He received an honorary Doctor of Science DSc degree from University of Burdwan in 2001. In 2014 and in 2001, American Physical Society presented him and the Esther Hoffman Beller Endowment Lecture Award. As a widely respected member of global particle physics community, he has been invited to serve across many international scientific committees. He was a member of the Program Advisory Committee of the Laser Interferometer Gravitational Wave Observatory, LIGO, USA. He has also served on the International Committee to review the KEK Accelerator Laboratory, Japan. He was a member of the International Committee for Future Accelerator Neutrino Panel, IUPAP Astroparticle Physics International Committee, OECD Astroparticle Physics International Forum, International Oversight Committee of Neutrino Experiments, Fermilab, USA. He was the leader of TIFR group in the D0 experiment at Fermilab, USA, which discovered the top quark in 1995. He was also the technical collaborator for the Outer Hadron Calorimeter project of CMS detector at Large Hadron Collider LHC at CERN, and led the Indian group in building the entire Outer Hadron Calorimeter detector in India. Over the last 2 decades, Professor Mondal has dedicated his efforts towards the development of a world-class underground laboratory in India for carrying out research in the emerging field of neutrino physics, India-based Neutrino Observatory, INO, which I mentioned in the beginning. The INO is one of the most ambitious and largest basic science projects in Indian history. A collaboration of more than 100 physicists and engineers from over 20 leading research institutes and universities of India has been formed under the leadership of Professor Mondal. Thank you very much, sir, for joining us. And now I'd like to request our senior professor, Professor Aparajita Bhattacharya, to please come up on stage and felicitate Professor Mondal. Thank you, sir. Thank you, ma'am. And now I would like to request Professor Subhashish Chattopadhyay to please come up on dais and join us. Thank you, sir. Dr. Chattopadhyay completed his MSc from the University of Calcutta and joined the Department of Atomic Energy in 1987 as a trainee of the 31st batch of Bach Training School. He completed his PhD in physics from Calcutta University as a researcher of VCC Kolkata After initial participation in nuclear physics experimental program at VCC, Dr. Chattopadhyay has been working as a leading member of VCC in experimental high energy physics activities at CERN Geneva, Brookhaven National Lab, USA, and currently at FAIR, Germany. Dr. Chattopadhyay has received DAE Science Research Council Award as an outstanding research investigator and the Homi Bhabha Science and Technology Award in 2009, and several group achievement awards from DAE. Dr. Chattopadhyay has been appointed jointly by the Department of Science and Technology and the Department of Atomic Energy, the Program Director of the Indo-Fair Coordination Center, IFCC at Bosch Institute, Kolkata, and an adjunct professor at Bosch Institute, Kolkata. This center is to coordinate India's participation at FAIR, Germany. Dr. Chattopadhyay, as the International Deputy Spokesperson of the Compressed Baryonic Matter (CBM) experiment at FAIR, Germany, has been leading a group of 17 universities and institutes in the country to participate in the experimental programs at CERN and FAIR. He is coordinating the effort at VCC of the development of advanced detectors for their applications in the India-based Neutrino Observatory and in the field of other applications. Dr. Chattopadhyay has supervised more than 20 students for the PhD so far. He has been elected as a fellow of the National Academy of Sciences, India. So welcome, Professor Chattopadhyay. Please give a round of applause for all our esteemed panelists. And now, felicitation. Now I'd like to request Professor Aparajita Bhattacharya to please come up on stage and felicitate Dr. Chattopadhyay. Professor Chattopadhyay. So now let us start the actual program, the panel discussion. So first, before going into the question answer round, I'd like to request our esteemed speakers to describe very briefly in a lucid manner so that you all can understand the basic objectives of all the projects. So first, I'd like to call Professor Shivaji Raha sir to please come here.
I'll take it. Yeah. Good afternoon, and it's a great pleasure to be here with the young participants in particular. And my job, rather our job collectively, is to try and impress upon you that physics is a living, thriving subject which will benefit from your future involvement in it. And the return is, I think those of you who would want to come into physics and make a career of it will be greatly benefited by it. Now, you have been listening to all the possible prospects as a physicist for the last 2 days. I won't dwell on it for too long. Today, we are concentrating on the mega science projects in which India is playing a major role and which holds promise for gainful involvement by many of you in future. You have heard that there are 4 major projects, but all of those are high energy related. There are a few other mega projects. And before I get into the description of those mega projects, let's get one definition clear in our minds. What does one mean by mega projects? Mega projects essentially mean that these work towards a goal which is extremely manpower intensive, cost intensive, and of a long duration. Cost and manpower intensive to the extent that quite often it is not possible for one institute or one university or even one country to really organize and run them. Sometimes that's because of lack of expertise or lack of resources. So people have to bring about international collaborations where everybody shares the cost, the responsibility, and ultimately there is not much competition. They act as complementary scientists in these projects. You have all heard of CERN in Geneva. Professor Shunanda Bandyopadhyay will talk in detail about the present activity of CERN in the Large Hadron Collider domain. But also one aspect one should remember about the history of CERN. CERN came about in Europe, which was really suffering from the ravages of the Second World War. So CERN came about as a beacon of collaboration between the, I wouldn't call fighting, but between the various nations which were not entirely friendly or amiable towards one another at that time. And those of you who have read a bit of world history would also know that 60s and 70s of the last century were the era of Cold War, intense competition between the Western Bloc and the Eastern Bloc. In that backdrop, CERN provided an environment where people could look for basic developments in science, generate knowledge without any political complications. Soviet Union scientists could also work at CERN without any animosity. American scientists and Soviet scientists could collaborate. So the amount of cooperation and diplomacy in international collaborations is also extremely important aspect. Now, I would just give you a very brief introduction to Is this legible at all? Okay. So there's a famous quote from Einstein that is, the strangest thing about the universe is that it is understandable. The human intellect understands the universe through scientific investigations,
explorations, and logic. No part, however, large or small, escapes our attention, and our quest for the physical laws governing all aspects of the universe comprises the ultimate intellectual endeavor. And that precisely is the object of physics. So this is a logo which depicted a conference, a series of conference exhibitions which were conducted jointly by the Ministry of Science and Culture and the Department of Science and Technology and the Department of Atomic Energy. And it was primarily prepared by the National Council of Science Museums about 5 years ago almost, 2018, 17, 18. And these exhibitions traveled to all the metropolis of the metropolitan cities of India, started at Mumbai, then it moved to Bangalore, then it came to Kolkata, and from there it went to Delhi, which was the closing part. And this highlighted India's participation in the physical sciences major collaborations in which India had made a stake. Beyond this, there are also a few other mega projects, namely the Human Genome Project, also the Climate Modeling Project, in which are also mega projects according to the definition that I gave you. It must involve a large number of participants. It must be time consuming. It must be resource consuming, and it must be a long-term project. Of the physics, in this picture, this is not very easily legible, but you have already heard the mention of RIC at Brookhaven. You have also already heard LHC at CERN and FAIR. There are a few other projects in which India has made tremendous involvement, namely the India LIGO project, the Gravitational Wave Detector Laboratory, the 30-meter telescope project, the largest optical telescope that's being built, in which India is a full partner. Another very, very large project on plasma physics, ITER, in which India is again a founding member. And of course, the India-based Neutrino Observatory that Professor Mandal will talk about. So of these, the high energy physics related projects are, once again, LHC, RIC, FAIR, and INO. Now, all of these have tremendous prospect for involvement in them of the young people, not only physicists, theoretical as well as experimental, but also people who work in engineering physics. And as a matter of fact, I'll just show you one or two pictures of India's contribution in the area of hardware to FAIR. And starting with the early days in the 90s, when India first started participating in the CERN L3 experiment and then also at Fermilab, we have really come a very long way. For example, earlier, our involvement was in providing either manpower or at best some low-end technology. But today, India is contributing to a large extent very sophisticated equipments, detectors, and also accelerator-based things. Dr. Chattopadhyay will tell you that India has provided the design of a very complicated magnet to FAIR, which the complications of the design were such that FAIR could not have done it themselves. So they gave us acknowledgement and financial credit for the design of that magnet. We are responsible for building a very, very vital equipment of the CBM project, the muon chambers, which is one of the primary ingredients of the entire experiment. So there are these prospects, okay? And I invite all of you to try and find out more. This will be extremely rewarding, and especially for young students, people who will get into undergraduate or postgraduate studies. For them, there is also a lot of scope of further and intense training at these international collaborations also. For example, FAIR has a project, a program called Get Involved, in which students can do summer projects at FAIR. And it doesn't really cost very much as long as there is an agreement between the students' institution and FAIR. Okay. So there are many such prospects, and everybody should really try and find out more about it. Once again, I'm most grateful to the organizers for asking me to come and talk to you about. I think we have spent our career chasing after some intangible truth. What are we all about? Why is the universe the way it is? And this finding out bit by bit, piece by piece, gives you enormous pleasure and satisfaction. I invite you all to try and be part of that experiment. Thank you.
Thank you so much, sir, for this enlightening talk. And now I'd like to request Professor Shunanda Banerjee to come up here and give us a very brief introduction of LHC.
Good afternoon, everyone. After such enlightening talk from Shivaji, okay, I mean, over such a broad area, I'll be talking about a very narrow region of science, which is called experimental high energy physics and the Large Hadron Collider. Okay. ঠিক আছে। Okay. Let me introduce the subject high energy physics to you. This looks for the fundamental constituents of matter and their interactions. Now, you must have known this gentleman whose photo is here. Okay, his name is Galileo Galilei. And what he says, okay, I mean, people can think about many things, but most of the things which people think about may not lead to the truth. The only way of leading to truth is trying to do experiments and trying to see, okay, if their thinking really matches with the results of the experiment. So high energy physics really does that sort of thing. That means, okay, you try to profess something and try to do an experiment to see if that thing is right or not. Now, what we try to do, এটা বেস্ট হচ্ছে এটাকে
এক মিনিট ক্রোমে তুলে দেন, ওটা এক্সপায়ার হয়ে যাবে। কি করা রয়েছে?
F11 এ exit হবে।
না, এটাই তো।
আচ্ছা, ফুল স্ক্রিন সেটটা
Okay. Now, this is some sort of a scale of things, and we the human beings are right in the middle of it. And if we want to look for the real constituents, okay, of the matter, we have to go down the things, okay, by several orders of magnitude, something like 25 to 26 orders of magnitude. And how we can see small things? You know, okay, I mean, to see small things, we need microscopes. And the resolution of the microscope has to be good enough, okay, to see them. So the only way to improve the resolution of the microscope, that means you need something which has got a wavelength which is smaller than the smallness which you try to see. Now, if you go to the smallest wavelength, means it is we have to go to the highest possible energies. And the only way we know to go to high energy is to use high electric field on some charged objects to go to high energies. And that's where the so-called accelerator comes in. And that's where we start from. So we accelerate charged particles. And obviously, the first thing happens is that, okay, if you want to accelerate charged particles, you have to apply very high voltages, and then you have to break down the voltage. Insulation comes in. So we have to do it the same high voltage, but do it repeatedly. And that's where we have the so-called linear accelerators and synchrotrons. And there's an important issue is that you need the total energies to be very high. So instead of hitting anything with a high energy beam, you try to collide two high energy beams on face on. So that comes the cost of the colliders. Now, to achieve the highest possible energy, one needs to make orbit larger and larger. And at at the same time, you have to make it more precise and precise. And this precision is something like a part in 10 million. So this needs, okay, that you have to have a very good civil engineering to do that. This needs a very high cost civil engineering. And you have to keep these particles in the orbit for a long period of time, and you do not want to lose them through interactions. So you need a very high degree of vacuum. And this means, okay, I mean, this is something like a 10 to the minus 13 atmospheric pressure, okay, that's what you put in. And you do not lose too much energy in the form of heat in the accelerating components or bending magnets. So you use superconducting cavities. That means you operate at temperatures which is almost the coldest temperature in the whole solar world. So these are the real technical challenges, okay, where you have to do experimental high energy physics for today. In addition to that, you have to look for very rare processes. And when you want to look for very rare processes, you need something very special things. And we have to also do limited usage of the computers, okay, where you have to remove the data. And you need a distributed computing system and a robust information exchange mechanism system. So you not only tend direction in civil engineering, electrical engineering, and so on and so forth, you also do in computer science and so in computer engineering as well. So this experimentation can only be a joint effort of many world-based engineers and scientists over the world, and from a large number of countries to break all the barriers of human knowledge. So you create a few centers of excellence in the world, and people from all over the world join their efforts for doing that. One of these places is CERN in Geneva, and there are a few other places in the world as well. Now, what we have learned, okay, as a basic constituents are something like this. And one of the first major effort in such a collider experiment was done by a group from Bombay, TIFR, who went to CERN to this particular experiment, which is this a large ring in which is a 27-kilometer long ring, and where electrons and positrons are colliding each other. And this is the lowest technologies which Shivaji just said, okay, this is the thing which we built for this particular detector. But this was not such a low-tech thing as such. We have to do it with the highest possible precision, which was available in Bombay in those days. Anyway, now we have moved to the Large Hadron Collider. And this is the place where protons at 7 trillion electron volt in energies are moving against each other, and they cross at the rate of 40 megahertz. And there is something which is called a luminosity, which essentially says how many events you are going to see per second. And that is also extremely high. You can see, okay, this is a very large number. It is 10 to the power 34 per centimeter square per second. So you see a number of interactions at every bunch crossings. And there are particles which are generated during each bunch crossing, say several thousand. Okay. So, and your interesting events are only one in several thousand trillion. So this is a thing which you have to wonder about. Oh, sorry. So you see a place where the detector shows interactions like this. Even in such interactions, we see something which is very, very strange. Okay, we see something which is something which cannot be explained by a standard model. So we see a new particle which is called Higgs boson, which was discovered in 2012 by a group of scientists from all over the world, and India was a good part of it. There are at least, I do not know how many, 6 or 7 groups from India, okay, who were part of this EMS experiment at the time. And we at Shah Institute of Nuclear Physics were a member of that. Okay. So I think we still have many burning questions. Okay, I mean, this is only a part of it which is relevant. And I think, okay, Nabo will say, okay, some other burning questions which is relevant in the field of neutrino physics. So only future experiments can answer some of these questions and many more. Now, this is one of the experiments where we are involved right now from India. You see there are 32 faculties and 22 engineers and 70 PhD students from 13 institutions in the CMS experiment. Okay, so it's a large number of people from India, more than 120 people from India who are participating in this experiment. And we have built various things in this thing. We have built a part of this outer hadron calorimeter. We built the first silicon strip detector in India, and that has gone in what you call a pre-shower detector in front of the electromagnetic calorimeter. And we have also formed detectors in front of in the muon detector system as well. So we have produced more than 110 PhDs over the last 10, 12 years. And they're employed as faculties in various Indian institutes in India and abroad, employed in big data science projects all over the world, and also doing their postdoctoral things. So one of the major contributions we have done in the computing system, the simulation, calibration, and high-level triggers. We have made many major discoveries in the physics, including the discoveries of the Higgs bosons. We definitely, as Shivaji says, okay, we operate in a large budget. This is about 119 crores over a period of 5 years. And this is for something like about 120 faculty members. So it is not that large if you divide the amount of money by the number of faculty members. And any other experimental projects may be costing more, okay, for that same period of time. Now, CMS experiment is not finished. It is continuing for the next, you can see, okay, there's a scale here. It is 2028 to 2042. So for the next 20 years, this experiment will be running. And this will be trying to see, okay, I mean, at least 10 times the amount of data which has been seen so far. So in that process, the entire detector has to be changed. So we are at the moment, okay, I mean, essentially changing all the detectors which is in here, and also some of the detectors which is outside here, only keeping the magnets as intact. And that will be doing, okay, for the CMS experiment. CMS experiment is not the only experiment in which India is involved. We are also involved in the other detector, which is called ALICE. This is a detector which has a different type of challenge. The different challenge is basically it tries to see not just proton-proton collision, it also sees proton colliding with ions and ions against ions. And the type of events which you see events like this. And you have to analyze events like that, okay, I mean, in this particular ALICE detector. This is not an easy task at all. But 13 institutions from India, okay, I mean, are participating in that. And they again operate at the similar level of budget, okay, for the next 5 years. As I said, okay, the emphasis of this experiment is look for the quark matter and establish the existence of quark-gluon plasma and study soft hadronic interactions in all these collisions. They contributed also in the constructions of very important components of this detector. And this is one of the components. This is the one of the detectors in the forward muon system. And the second station of this thing, okay, I mean, that has been constructed by the Shah Institute of Nuclear Physics. And also they have built up the photon multiplicity detector at the VECC, along with some other groups. And also they made the readout chip, Manoj, which has been used in many parts of the ALICE detector. Now, these things are not the end of it. We are only at the beginning, so we need a long-term planning period in this area for future project. And this will be always based on the current findings and the limitation of technologies. The plans to progress is to increase in 3 different areas: in the overall energy, that is the energy front; in the intensity front, which is called the look for rarer process; and also the precision of the measurements. So it is really high time to hand over the torch to the future generation of physicists, okay, which could be some of you, to do the future research. Thank you.
Thank you so much, sir, for such informative introduction to LHC. And now I'd like to request Professor Nabakumar Mondal, sir, to please come up on stage and give us an idea about this Indian Neutrino Observatory project. So, it's okay, sir. Absolutely fine.
I'm not using any slide because I think let's just talk a little bit. So first about this mega science versus normal science. I think I would say that, see, you ask me, I don't want to call it mega science. It just happens to be that, as Sunanda has pointed it out, because it's a large number of scientists are putting together their effort and they are trying to answer a single question. Now, this is what is special about high energy physics type of experiments. So I will call it actually, what is high energy physics experiment is, if you ask me, so I will borrow or some title from Hillary Clinton book, what she wrote, that it needs a village to raise a child. That's the title of her book. So I will call it, it needs a village to do an high energy physics experiment. So what does it mean actually? So that's actually already pointed out by the previous speakers. To do an high energy physics experiment, let's say accelerator based experiment, you have to design, you don't get anything. Experiment, if you see that you buy your instrument from the shelf and then start doing experiment, that's not how energy physics experiment is done. So you start going to the drawing board, you design everything. You first design everything, you design the accelerator, and then you first, of course, before the design of the accelerator, the theoretical physicist will come and tell you that what kind of accelerator you need to do certain physics. So if you want to see Higgs boson, for example, what is the energy you need for an accelerator? Then the accelerator physicist will design it. Then there will be detectors people who have to build the detectors. Then electronics people will come. They have to design the electronics. Then the software gurus are required. They will have to design the software. And ultimately you do the analysis. So you see, all different kinds of people have to put together. They're not physicists only, may not be. So you don't have to think that you have to be a physicist to do an high energy physics experiment. You can contribute being a software specialist. You can contribute being an electronic specialist. And this is all putting together what was actually our idea of building something in India. And that is where the India-based Neutrino Observatory also came as a right. Now, neutrinos is, as many of you know, probably, neutrino is also a fundamental particle, like quark, lepton, you have heard electron, positron, like neutrinos. But neutrinos have some special characteristics that make it special. One of them is that it's very difficult to detect. It's penetrating. It will go through the whole earth without doing anything. So that is a disadvantage because it is very difficult to detect it. So that is one disadvantage. But there is an advantage in it also. Because if you want to see inside core of the star, what is happening, okay, you can only see through neutrinos. You can't even, light will not come out from there because they will get scattered so much, they will not come out from the core. So that is why important is neutrinos. Actually, some two weeks back, you have seen that is a press conference, probably you have seen in the news, it was there, that this is for the first time, they have mapped the galaxy, our galaxy, using neutrinos, actually. And also, if you want to understand what is happening at the early stage of our universe, you have to depend on neutrinos. Because what we see of the universe is up to the time when universe was only 3,000 years old. So all these different questions you can answer with neutrinos. So on that basis, we started INO, India-based Neutrino Observatory project. But the main thing that we thought is it will give us an opportunity for our engineers to design our own detector. For the electronics people come and make electronics, you design everything for so everything will be done. And the students, they can be, of course, you can go to CERN, you can go to FAIR, and but here there will be a detector in the country where you can always go and spend your summer, spend any time, anybody can go there. So these all put together, and not many students can go to CERN and other places. So we need something. It's just complementing what we are doing elsewhere in the country. So on the basis of that, we have planned to do that neutrino experiment. And also another reason that we have a long tradition of doing neutrino physics. Neutrino physics is one area we have contributed a lot in the past. Even in the 40 years back, actually, 45 years back, we have contributed a lot. And for example, the first atmospheric neutrinos was detected in India, in Kolar Goldfield. And that was also an international experiment. So at that time, in 1960s, people from other countries came here to do experiment in collaboration with us. So that was our tradition that time. So we thought we should go back to there. So that is also another reason why you want to do the neutrino experiment. But I'll tell you something, it's not easy. So this is all good, nice, we want to do exciting things, but it's not easy. In fact, this experiment is stalled, it's not progressing much. You know why? Because we went there and we want to build a tunnel under a mountain, and immediately the politicians and activists came and they stopped it and they stalled the project. They went to the court, says that these neutrinos will be coming from somewhere else and they are bad for human beings, so we should not allow this to happen. In fact, that is why even the project is not progressing much even today, even after we have got the money from the government of India 7 years back, but we have not made any progress. So this is very difficult to make a project in the country, but probably we should, and you should be ambassador, you should talk about science. When there is a pseudoscience, people talk differently, irrational things. You also should be able to explain to them that what we should do in science and why we should do science. That is also very important. I think I will stop here at the moment.
Thank you so much, sir. It's really nice to hear about this Indian project, and I hope that in future, this sort of challenges will be overcome. Thank you very much. And now I'd like to request Professor Chattopadhyay to give us a little introduction about RIG project. So.
Okay, let me go back to the definition again. How many of you have watched Oppenheimer? 1, 2, 3, 4, 5. So there is a name of project, right? Oh, okay, 6. Okay, so there is a name of project, Manhattan Project, right? And there are the name of scientists. I think you must have seen all the scientists there: Einstein, Bohr, Heisenberg, Oppenheimer himself, Lawrence, and all of them were Nobel Prize winners, right? Is it a mega science project? Because there is a number, $2 billion. So which if you take in today's price is like 20,000 crore. So is it a mega science project that we are talking about? For me, it's not a mega science project. It's a mega technology project. That means they wanted to, all the physics were there already. Everybody knew E equal to mc square, energy can be converted, uranium will happen, fission was known. So only they wanted to make the bomb. So they wanted to detonate, they wanted to put all the energy together and show you that it works. So in the list which Professor Rahar showed, there are several mega science projects. There is one which is called ITER, International Thermoelectric Energy Reactor. It is something like you generate energy from fusion. So this deuterium, which is the source of energy inside sun. So that also to me is a technology project, mega technology project. So these are all mega projects, because when LHC started at CERN, there were 2 people who filed a lawsuit in Hawaii. You know why? They said that the LHC should not be allowed to start. You know why? Because they said that these guys are saying that they will recreate the universe. And if they recreate the universe, they will recreate a black hole. And this black hole, the gravitational pull would be so much that everybody will just go away. So then some people, of course, said that doesn't matter. Nobody will be there to complain. So what is there? So, but then the judge said it is not in my domain because the things are happening in Europe and it is in US. And then finally CERN had to prepare a voluminous report to kind of show that yes, we will all be there. And then only they got the green light. And today we are here, right? LSC is running for last 10 years. And that is what is the mega science. So to me, mega science is something which addresses the fundamental question, which is not known yet. You may get answer, you may not get answer. Somebody got a Nobel Prize for Higgs boson in LHC, but people have been trying for last 20, 30 years. So that is what is to me is it's a science project, and of course it's in a mega scale. So now the one which I am trying to kind of talk about here is not in Europe, but in there is a place called Long Island, which is near New York. This is called Brookhaven National Lab. Like you have heard about Livermore Lab or you have heard about Los Alamos Lab. There is another US lab, Department of Energy Lab called Brookhaven National Lab. So in that lab, this is happening. And then the fundamental point, this is a mega science project, not of that scale of LHC, but it's smaller than that. But the fundamental question that we are talking about, you see this picture, it starts with Big Bang, which is time t equal to 0. And at the end, we are here like 15 or whatever billion years after that Big Bang, right? So let's look at somewhere which is 10 to the power minus 5. You see 10 to the power minus 5 somewhere? Now, I like this picture, not because it is very colorful, but because there are so many questions there. You see the questions? So these are not answered. So it is essentially an artist view. It is not a scientific picture in that sense. So you have to answer those questions, then only it will become scientific. So Professor Banerjee said it that you have to experimentally prove. So there are theories that what was there in 10 to the power minus 43 seconds, just after the universe was formed. So then the forces got separate. There are 4 forces which govern us, right? Electromagnetic, gravitation, weak and strong. So they were all together. So all the particles or whatever was being governed by those forces together, and then they got separated. But now my attention is on 10 to the power minus 5 seconds. Now you draw a line on that. Just draw a line, imaginary line. You see, there are things like Q, E, W, Z, gamma, and all those things, Z. And on the right side, there is no Q, there is no G. You know what? Q is called quarks. What is quark? You break bricks and break, you reach molecule, and then you reach atom, and then you go to the nucleus, then you get proton. You break proton, you'll get quarks. There are 3 quarks. So that is so this is the fundamental building block that is known so far. But when universe was formed, quarks are all free. You will not get any free quark today. If somebody tells you that give me a bag of quarks, you will not get it. But give me a bag of electrons, you will get it, because electrons are free. But you will not get it. You will get a lot in X-ray tube electrons. So there is no problem with electron. So the electron which was there, E, they are still there. But you see the Q, they are not there today. So as if something happened, they got caged. Inside what? Inside protons and neutrons. So protons and neutrons are made of quarks, but they are not there at the beginning as cage. That is why these are called confinement of quarks. This is a very special property of quarks, that when you bring them together, they are almost free. If you try to take them apart, the forces go higher and higher. You can't take them out. It is opposite to the electromagnetic force. Like if you take 2 charges apart, force go down, right? But in this case, if you try to take them apart, it will go up and up and up. Some people say it is like husband-wife problem. So this is what is the confinement. Now this is a theory. People said that they were deconfined in 10 to the power minus 5 seconds. After that, protons were formed. But this is a theory. Nobody is there to prove it. So the thing which I am going to tell here is a mega science project which is trying to prove it. That something like that, where all the quarks and gluons is something like glue, which acts between quarks to have this force working. So these quarks and gluons are all free, like a kind of soup of quarks and gluons. And after that, protons came out, and you get proton today, neutron today. So this is the project that we are talking about. So you can see how you can get there. You cannot recreate the universe, right? And go to the 10 to the power minus 5 seconds. So there are 2 ways people said that you just take a heavy ion like lead. Lead has 208 protons and neutrons together, and just heat it. That means give a lot of energy to that lead. And then by E equal to mc square, it will create many more particles inside. That energy will get converted to particle. And you will see this is the soup of quarks and gluons. This is how you can get it experimentally. Or otherwise, you have to compress it. That means put together inside one proton, you pump 7 protons. And then also it will look like this. So experimentally, what people say that you just take 2 lead ions and just collide with very high energy. Energy means almost the velocity of light, 99.99999% of the velocity of light, and just collide. They pass through each other, and in the middle you have only energy, and that energy will form quarks and gluons, and that is what was there at the beginning. So this is what is called recreation of universe. Now I will not go into details because these are all going on since this kind of experiment is going on since 1984 till today. And I am talking about something which is called RHIC, RHIC, Relativistic Heavy Ion Collider. It's Brookhaven National Lab, Brookhaven in Long Island, New York. It's still working since 2000, and forget about all the other numbers. Now, this is another thing which I think Sunanda has talked about. If you want to look at a cell, which is like a micrometer, you need a microscope. If you want to look at a DNA, which is like a nanometer, 10 to the minus 9 meter, you need an electron microscope. If you want to get hold of a nucleus, which is formed of protons and neutrons, you need accelerators. This is somewhere here where I belong, maybe 1 or 1.5 hour journey from here in Salt Lake, there is a place called Variable Energy Cyclotron Center. And we have in fact 2 accelerators there. One is superconducting, another is normal. How do they work? The charge particle moves in a magnetic field because this is the property of charge particle. And every time it moves, you give an electric field on the path. As you give electric field, it gets in a longer path. Then again, it's like Chakti. It goes on and on and on. And when you have enough energy, you just let it come out. This is how cyclotron works. This is what we have. But then the problem is cyclotron, you cannot raise the energy too much. After some time, it will start radiating, it will, all sorts of problems will happen. But then the solution is that you let them move in the same circle all the time. You allow it in the same circle. Don't allow the circle to become bigger. And then keep pumping energy. And that is called synchrotron. And all that we talk about is RHIC, Relativistic Heavy Ion Collider or Large Hadron Collider. These are all synchrotrons. So these are accelerators where you can make energy almost at the velocity of light. And then when you want to take it out, let it out. One is going in clockwise, another guy is going in anti-clockwise, put the magnets and let them collide. By collision, it will create the universe. How do you know that it has created the universe? This is what is RHIC. It's not as large as CERN, which is 27 kilometers. Which Sunanda talked about. It is between Switzerland and France. So 100 meters below the earth, there is no border. Nobody asks you that do you have a passport or visa. So there all the things are moving. You know, there is a book, Angels and Demons. In Angels and Demons, the protagonist went, his job means he wanted to destroy Vatican, right? Because he had some problem with that. And then the weapon he wanted to use was antiproton, antiparticle. He wanted to drop antiparticle from top, and Vatican is particle, it will destroy. That is what was the theory. So he knew that this antiparticle he can get from only one place, which is CERN. So he went to CERN. And he went down there, and this is very fantastic, right? That there was this identification, right? Iris. Identification. So he took out the eye from the security guy and put on that. I do not know how many of you will believe it. And then he got that antiparticle in a bottle. Then I don't know how many of you will believe that either. And then he went there, and then Vatican is still there. So he must have not been successful. So, but then there is a statement that guy said when he went to CERN, he was given a tour. If any of you, you will also get the same tour. I don't know whether you'll go able to go to underground or not, but he will be given a tour. He made a statement. Oh, I understood. That means CERN has dug tons of earth to collide two hair-like particles. So that is the ultimate job that we all do. So far as accelerator-based mega sciences project. So this is what is RHIC, which is in Brookhaven, which is maybe 2.2 kilometer ring, not 27 kilometers. It's smaller one. So energy is also smaller. If you see, there are in the tunnel, there is a tunnel, there are the magnets, which essentially moves the things, and these are all superconducting magnets, because you cannot have too much magnetic field in the normal conducting magnets. And then you collide two, and then this whole energy will create particles. How many of them? Around 10,000 particles will be created. And from there, you have to say that yes, whether quartz and gluon soup was formed or not. That is what is the question that we all are trying to address. And we use what? We take photo. It's like your mobile camera, right? 25 megapixel. So here billions of pixels, and you take picture of everything. 10 to the power 7 collisions per second, that is happening. And you take picture. So think about a camera that you have, which will take 10 million pictures per second. And this is not hard of. If it is not hard of, then you have to develop it. And that is the challenge of all the mega science problems. One thing I am just telling you quickly, all those whatever experimentalists say in high energy physics, they say they do a very simple thing. What they build is like onion, like peeling onion. So there is layers of detectors. In the middle, so these are the layers, these are different names. Now let's say you want to detect electrons which are produced. So let electron field in a magnetic field, it's a charge particle, it will move and deposit all the energy inside a lead. If it happens to be a photon, it will not give any signal to you. There is no charge particle, but it deposits energy. If it happens to be a proton, then proton will move, bend on the opposite direction to electron. So you need a magnetic field and you need different sets of detectors for different particles. You have to make one thing sure, that don't put proton detector before electron detector, because all the electrons will get absorbed even before you detect proton. So that is the only challenge. And there is one thing which neutron, what will happen? It will not give anything to you because it's a neutral particle. Muon is something which just coming out of you all the time, and it will charge particle. And then the one which you do not see at all is neutrino. So this is the homework to all of you. Go and ask anybody, how do you detect neutrino then? Because it doesn't give any signal anyway. And it come out of everything. So this is how this detector works. And there is another anecdote I say. Everything is available in Google, right? So you look for Rutherford. Rutherford is the one who discovered the atomic nucleus. And you will see that paper, Rutherford's paper, E. Rutherford. There is only one author, right? E. Rutherford. And we are all doing nuclear physics now because we are colliding two nuclei. When you do in VECC experiment, which I did, something like, I have my name there somewhere, S. Chattopadhyay, 15 people. Then I went to Brookhaven National Lab, which is the name of the experiment is STAR, solid tracker rate. There are 250 people. And then I went to LHC, there are 1,000 people. So the pages are only for names. This is for not for nothing, because you need so many people. You start from physics, then it becomes like Sunandada or Navodar said, it becomes an engineering project. And after 20 years, maybe you do some physics and get something. So there is a picture of all those collaborators standing somewhere. These are the 4 experiments in RIC, where they take about, so these are, see the people around in the real experiment. And LHC, there is a paper that somebody is handling a baby while taking the picture. So then the statement says, these guys will build the detector and he or she will analyze the data. Because that is how it will take. So that is why it is mega science. So here we have one detector which we have built. And this is what is sitting here, built in Calcutta. This is called photon multiplicity detector. It is not time to discuss all details, but it is challenging. We have, again, it's like you have to have a collaboration, and these are the collaborators: VECC Calcutta, Science Institute of Nuclear Physics, Bhubaneswar Institute of Physics, Rajasthan University, Jammu University, Punjab University, IIT Bombay, Aligarh Muslim University, Guwahati University, IIT Indore, Bose Institute Calcutta, NISAR Bhubaneswar, and the Jadavpur University, Calcutta University, Aisha Tirupati, DAV College, and who knows, 17 might be Adamas University. And this is the lab that we have, where we build all those detectors, which we took to Brookhaven and then installed it there, took data. And this is their data, means the detectors are being tested before you install in the place. And this is taken from CERN. Just to give you an example, if you take this data, because these are all digital camera, right? So you can put the data in a floppy. And I don't know how many of you know about floppy nowadays, but you take floppy's highest density and then put one over the other. And the data that LHC will make in 1 year, that will be the height where airplane flies. And somebody tells me now you find quark gluon plasma there or Higgs or whatever. And it will take generations. So the funding agency will say, forget about it, I have given you €1 billion or dollar. So your means it is something like that story, na, that amar ki bole apni kharch korben apnar nati ese taka debe. It is something like that, right? So the only way it was solved, but CERN discovered it, announced their discovery in few months, maybe a year time, because all the computers were connected by high-speed internet, like power we do. It's called grid computing. So you see, we are talking about 27-kilometer ring. It's a civil construction. We are talking about a structure of 11,000 ton. It's a mechanical like anything. All these detectors, you have to have electronics, of course, physics of it. And then you have to analyze this data. And then only maybe you can go to Stockholm on one day. And this is one of the result from Rick. As I said at the beginning, that we want to create a medium of lead and lead colliding and try to see in the middle if there is quarks and gluons all deconfined. That means they are not inside protons. It's a soup. So this is the theory. Somebody said that if you create a medium and if there is a quark, because quark is not free. Quarks, ultimately, it comes out like protons and neutrons. That's called jets. So these jets will come out. One jet will only come out. Other guy will not come out. If the density is so high. It's like energy loss. It's so density, nobody can come out of this room. But the guy who is in the side may find a room and come out, because they come in twice because of the momentum conservation. So one guy will be stopped, another guy will be seen. And this is the result that you see. This is one guy. This is proton, both are there. And for heavy iron, it is gold on gold. You see one, which is blue one, and there is nothing on the other side. So this is one of the most important results which was confirmed in LHC again. And LHC also, you see this one jet, you see, don't see the other one. So this is where I end. So exciting efforts to unravel the mystery of universe. So that is why it is mega science, not mega technology. And of course, there are engineering. We start with science motivation. We do all sorts of engineering. No scientist will be there by that time. And then you come back and start interpreting your data. And everybody is welcome to join. Thank you.
Thank you so much, sir. It was really nice to hear so lucidly about this project. And now I'd like to request all our panelists to please come up on the stage if possible. And now it's time for the question answer session. So students, if you have any questions, first let me ask all of you, or teachers. Okay. So Mike, please.
Sir, my question is the Higgs boson completely responsible for the mass of everything?
Boson is said to be responsible to explain the mass of elementary particle, not your mass or my mass. Higgs boson will explain electron mass, quark mass, and particle which is fundamental. Now, there is a thing is that, for example, proton, it consists of 3 quarks. Now, if you take a mass of proton in terms of energy unit, it's 1 GeV, 1000 GeV, 1000 MeV. Now, so power 1 is 300 MeV around, 330. But if you look at the Higgs mass, Higgs explain only 5 MeV. That means Higgs doesn't explain the complete mass of proton even. It explains when a quark is free, when an electron is free, then you can explain using Higgs mechanism or whatever you have. So, do you want to add anything?
we better say what the extra mass comes from.
I think that was his question also. What's the origin of that extra mass? So if Professor Raha can answer.
No, that where the total mass of the hadron comes from is something we don't understand yet. As Dr. Chattopadhyay just mentioned, Higgs explains only about 2% of the mass that is required. The rest 98% of the mass comes out of the interaction of these particles, which we still do not understand very well. Does that answer your question?
Any other question from
I hope-
anyone?
I hope you will sometime try to answer that question.
Good afternoon, everyone. My question is that sir said that the first neutrino was discovered in India. Then why can't we reason this as why are they stopping the neutrino project in India? If it was first found in India, then we can go on with the projects.
First, let me just to tell you correctly. It's not the first neutrinos was detected in India. I said first atmospheric neutrinos was detected in India. First neutrinos was detected in United States, okay, by Frederick Reines, as you know, probably have read, in 1956, and that's what he detected the first neutrinos. And the KGF experiment was detecting the first atmospheric neutrinos in 1965. Okay, so that is the difference here. Of course, and that is what we are trying to explain to people, that India has a rich history in doing this kind of cosmic rays and neutrino physics. So we should continue that tradition, and that is one of our message that we are taking to the citizens of the countrymen that allow us to do the experiment. But there are, see, I think why I said that one, that you must remember that one. There are various forces works in a complex place like India, and there are activists and different kinds of activists. And I used to always think that activist is a good thing, and I know they're doing good thing. But just to keep your, keep and watch on that one, because there are people who are doing for different interests. And why these people are doing this, I don't know. And there are maybe their reason, but I know a certain politician, because they need some platform. They need something that they can go and excite people. And so we scientists are soft target. So they know that we have not much voice or not much weight. So they can hammer us with something. So that's what is happening actually.
Thank you, sir.
That's not entirely correct, Novo, because you know the status of the TMT, the site controversy in Hawaii. So it's universal. It's not only Indian. It's not only in India. Sure. And I think the responsibility, the onus lies on us to make it clear to the general people that what we are doing is primarily for the good of the society. There is a misconception in the society that these scientists spend money and effort and all these resources for something which will be no good to us, no good to the society as a whole. So why should the taxpayers' money go into that? And that is something which, a misconception which we have to dispel. We have to show that this has benefit to the society as a whole, not only just enriching us in knowledge, but these all have also technological spin-offs. For example, it was mentioned that this grid computing that Dr. Chattopadhyay mentioned, the entire origin of the internet today, the World Wide Web, came out of the necessity of CERN research. And you probably can't think of life without web now today.
There are many other things. Okay, for example, okay, I mean, if you go to any hospital, okay, I mean, and you try to see, okay, all the nuclear medicines, all the MRIs and CT scans, okay, I mean, they have positive effects, okay, from all this research.
Definitely. So any more question? Kullan.
So is it safe to say that the Big Bang theory supports the theory of multiverse? So is it safe to say that the Big Bang theory supports the theory of multiverse?
Multiverse. Well, the Big Bang happened in our universe, according to our present understanding of cosmology. Multiverse is something which we do not know any way of proving as yet, experimentally. So until there is a way to establish the multiverse theory experimentally, I refuse to spend time discussing it. Primarily because the philosophy that any physicist takes is that every theory, for it to be respectable, has to be falsifiable. Means that it must give you some property, predict some property, which if you experimentally measure and it doesn't turn out to be so, then you know that the theory is wrong. Okay? That was essentially the state of quantum mechanics in the early stages, until Bell came up with certain inequalities which prove that if quantum mechanics is correct, then these inequalities must be correct. And that has been proven to be correct at the beginning of this century, or when was the line aspects first result? 95 or 96? Yeah. So now we have those experimental proofs, and that's why last year's Nobel Prize in Physics was given for quantum entanglement. Now, with multiverse theory, I don't know of any such prediction which can be tested yet.
Thank you, sir.
I just want to add, okay, even general relativity was not proven, okay, till the bending of light was seen. So Einstein didn't get the credit of general relativity for a long time.
My question is that, okay, currently how we study particle physics is we try to collide things inside of particle colliders, right, by accelerating them. But I suppose when you look into the vast sky, we can find stars that inside which there would be collisions that are frequently happening at very high energies. So what is the possibility of studying them for, you know, for new events that might occur, new phenomena and so on?
So one I told you actually, that is exactly, for example, I gave you that report that came up, or scientific discovery that came up only a couple of weeks back, is that the neutrinos, they have mapped the neutrinos to our galaxies, actually, to see that where the neutrinos are coming from. So now exactly that's the point, that we don't know yet clearly, whereas these extremely high energy particles, see, we can only collide now at, Sunanda has pointed out 7 TeV and 7 TeV actually is there, but much higher energies are getting, particular accelerated in the universe. And how they are, I mean, we have theories, of course, how they are getting accelerated, but we have not even identified, been able to find those sources, right? The one reason for that is that most of these cosmic rays they are coming from are charged particles. And when they are charged particle, in the magnetic field that around when they are coming, they will get bent. So we will not know, really speaking, where the particle is coming from. We don't know where is the direction is source. Neutrinos help you in that direction, because let's say inside those extremely accelerating, where particles are getting accelerated in certain places, the neutrinos are also have to be created, okay, along with gamma rays and other. And neutrinos, because it is neutral particle, it will come straight to you. So if you're detecting those neutrinos, you will be able to find out which are the possible sources. Once you have identified those sources, then you can use other, studies and so on, and correlate them to find out how they are getting accelerated. So this is one thing, but maybe Sivaji.
I want to add another thing, which is the complementarity of these two that you talk about. One is macrocosmos, another is microcosmos. You have heard, I'm sure you have heard about this gravitational wave discovery. And there are two kind of sources. One is two black holes collide and gravitational wave. Another one is two neutron star collide. When two neutron star collide, it will also create gravitational wave, but at the same time, it will create photons. So that this is the signal that it comes from neutron star. But how are the neutron star core look like? When something collide, what is the theory of it? Nobody knows. It's like you see gravitational wave, so something must have two big objects collided, and then you see the wave out of it. Now, the experiment that Professor Raha, for example, talked about, which is coming out in FAIR, where two nuclei collide and at very high density, not at very high energy, so that one goes inside the other, it creates mini neutron star. So you essentially create neutron star in the lab. And those neutron star and these neutron star must be similar, so that the theory which you generate here, looking at every many billions of neutron star collision you create, and then you put there, they should match.
Thank you so much, sir. Any other question from any students?
Good afternoon, sir. Sir, I have started reading something about gravitational waves. So can you speak something about what you mean by the ripples in space-time fabric? So what is meant by space-time fabric? Like, will it be anything that we can visualize something or like?
Yeah, visualize, of course, because unless you visualize it, you won't be able to measure it. Okay. And so what happens is space-time is a concept. Space you can understand very well, right? Now, space that you know is three-dimensional, right? It has length, it has breadth, and it has height. Now, if I just take a two-dimensional projection of it, okay? So let's say that I don't know anything about height, okay? So everything that happens on the floor, okay? So the height is imposed on it. And now I can rotate the axis and make the ceiling, the floor, okay? And so on, okay? So that's why these three-dimensional spaces are orthogonal to one another. And time, on the other hand, is a slightly different dimension. Okay. So when one says space-time, a four-dimensional entity, it just means that this is actually a mathematical construct. But anything that happens, every event is a point in this four-dimensional space-time. Okay. It has a location and it has a time when it happened. Okay. So that's why it is mapped in this four-dimensional space-time. Now, this space-time, if due to the passage of a gravitational wave, this space-time gets distorted temporarily. When the gravitational wave passes, the space-time changes. So any object which is embedded in this space-time will suffer a distortion. Okay. So that is precisely the kind of thing that you are measuring. You are measuring the change, for example, in a rod, okay, which you are trying to measure the length of, okay, and due to the passage of the gravitational wave, its length changes. And it changes to the extent of the order of 10 to the minus 6, 17 to 10 to the minus 18 centimeters. Okay. And that's precisely why it took so long to detect the gravitational wave. You really had to have the accuracy to measure such small changes in length. Does that answer your question?
Sir, so suppose if in this fabric there is to a large extent distortion, such that if since we are calling it a fabric, so it is possible that for a fabric to fold it like this, so does that create something like a wormholes or time travel?
Who wants to venture an answer? Well, okay. Wormhole is actually I can't, well, it's still at the level of science fiction. Okay. Even though I myself have of late written a paper in which the production of wormhole is predicted. Okay. But that is something which, once again, let me go back to my own principle that unless I can predict a falsifiable signature, I don't want to talk about that. Okay?
Yeah. Science is something which is experimentally observed and verified. If you only talk about something which cannot be experimentally observed and verified, that is not science, according to me.
Remember, many people will not agree to that.
Especially in India now.
Yes.
That is the bad luck of Indians.
Sir, I have another question. So we have heard a lot about artificial intelligence and machine learning. So what is the role of artificial intelligence in on the mega projects that we have heard or LEGO?
No, it goes at every level of the thing. Okay, so I said, okay, we have to find signatures of things, okay, where it happens one in several trillions. Now, general intelligence, okay, I mean, if you try to dish out a signature, okay, which is one in several trillions, it will take ages, or I do not know, you will never be able to solve it. So artificial intelligence used for that. So when it tries to take any data, okay, from any experiment, artificial intelligence is used. When you try to analyze anything from the thing, okay, we utilize artificial intelligence. So we use artificial intelligence at all levels.
It's not only experiments. I think the accelerator itself, because the huge 27-kilometer ring with so many magnets and so many systems put together, you just can't do it. Means just normal iterative procedure. You have to have some intelligence put into the machine. So artificial intelligence is used in mega science almost everywhere.
So maybe you wanted to know. See, for example, you see that you saw that they're showing pictures of events, right? So all those particles colliding and so on. So it's just picture. So it's just, you are there. So if I show you two pictures here, one is dog and one is cat, you will be able to distinguish which one is dog, which one is cat. Now they have billions of such pictures of Higgs or some background or this or that, so that if they have to go and scan each of them and then find out which one is Higgs and which one is not, it will not be possible. I mean, okay, actually in the early days, when started looking particle, not too much back, maybe 30 years back, it is actually physicists used to sit in front of the terminal computer and they to see which one this event is, whether it is a W boson or a Z boson or not. That was done actually in 1980s actually. But it's not possible actually now. It's so complicated. So that's why now you train the computer, giving them many pictures of computer generated Higgs boson or something else, and say these are Higgs, these are Higgs, these are Higgs. You just train yourself, and these are, and then you give an unknown event and tell computer, now from the intelligence that you have, you find out which one is Higgs, which one is not. And that's how they do little bit.
That is not the only place where it is used. Okay, say for example, okay, when you try to do an experiment, you do not go to get those pictures. You get essentially bits of the thing which comes from the thing which is a digital pattern. From those digital pattern to get to those pictures, that is again where a place where artificial intelligence is used.
Thank you, sir, for this wonderful discussion. I wanted to know that I don't have any analytical understanding to this, that the 85% of the matter of the universe is made up of dark matter. So when we collide in the fundamental level, in the Higgs boson, hadron LHC, and do we get any information about what that dark matter may be comprised of?
So far, there is no evidence. Okay, we're really trying to look for it. There is no hard code evidence for dark matter in collider experiments so far. The only place where dark matter is predicted are through gravitational interaction.
It's not 85% dark matter. Actually, from our present understanding of cosmology, which is not theory, on the basis of real experiments, observations, we know that all the matter that we see around us, which takes part in nuclear, electromagnetic, and other kinds of interactions, is only 4% of the total energy of the universe. Then 23% of the matter, which is called the dark matter, it has a property that it clumps. That is called cold dark matter, but it's dark because it does not emit electromagnetic radiation. So it does not take part in any of the interactions, except for the gravity. You know that somebody talked about the standard model. There are 4 types of basic interactions: okay? Strong, weak, electromagnetic, and gravitation. Okay? So cold dark matter, this 23%, participates only in gravitational interactions. Okay? No other. That makes 27%. 73% of the remaining matter, remaining energy, is something about which we know very little, except that it must be very smoothly distributed. Okay. And that is what is called the dark energy.
So is this distribution homogeneous? I mean, according to...
Yes. Yes. Yeah, because dark matter, as I said, it's clumped. Right? So it's clumped means that there can't be a homogeneity as such. Well, on a very large scale, it could be homogeneously distributed, but it's not uniform. Okay. Dark energy is, because it has no structure, no clumping properties, it's homogeneously distributed.
By the way, science is something, okay, which is based on certain beliefs. Homogeneity is one such belief. And it is, there is still some doubts about homogeneity per se. It may not be true.
Yeah, that depends on the interpretation that you put. The averaging process may have not been accurate.
Regarding this, I have a small question. I don't know if it's scientifically correct or not, that if there is a light wave and it has an electric field and magnetic field, and in one side, if we have higher concentration of space, I mean, it's like a massive object here, then relate, and if there is a bending of light, using normal Riemannian calculus, that bend, then in the left side, from the axis of the wave, the left side supposed to have shorter this oscillation of electric field. I don't know if I'm able to explain it. Like if the wave is moving this way and there is a massive contraction of space here, then this oscillation of electric field, this electric field on left side should be shorter and here should be larger. So can high energy physics explain that? I don't know if I am able to explain this because it is not my question totally. I saw this from PBS Studio, a video. I can share that.
Okay, Shobik, later on, you can discuss with that. Yeah. You want to ask a question? Okay.
Does the dark matter exist in every galaxy?
We definitely know that spiral galaxies have dark matter. For example, our own Milky Way definitely has dark matter. Okay. There aren't too many spiral galaxies in our vicinity where we could do the rotation measurement that accurately. Okay. But I think almost all rotating galaxies, especially spiral ones, show the evidence of cold dark matter.
Okay, so any further questions? Okay.
Good evening, sir. Can you please say something about the one-third solar neutrino in discovery few years back or on the topic? Yes. One-third solar neutrino.
The problem. So that was actually solar neutrino problem.
Yeah.
So what was saying that, we know the luminosity of the sun. Okay. So from the luminosity of the sun, you can calculate what will be the flux of neutrinos that will be reaching at the earth from sun. Because, for every 26 MeV of energy, that should be 2 neutrinos. So we know that. So that is what it is coming here. So now, from there, we knew the luminosity. So you calculated, Bacall calculated that how many neutrinos should be expected. And Ray Davis, who did that experiment in a mines in US, he was measuring how many neutrinos he is counting. And he found that roughly 1/3 of the neutrinos he was getting than expected. So that became a solar neutrino problem or solar neutrino puzzle, that we expect 3, but we are getting 1. So that was the puzzle for many years. So then what will be the suggestion? Then of course, by that time, suggestion was also there, Monte Carlo, and given the original suggestion that maybe neutrinos are oscillating. That means in the sun's core, when the hydrogen is burning into helium, what you get is electron neutrinos. Okay. So what Ray Davis was trying to find out is electron neutrinos. But if, for example, that neutrino oscillation, they said that while coming from sun to earth, the electron neutrino has converted into a muon neutrino. And Ray Davis was not looking for muon neutrinos. So some of those electron neutrinos converted into another neutrinos, another species. So he was not looking, so he was not finding them. So then the solution came, then somebody came up, then okay, we will do an experiment which can detect all 3 different kinds of neutrinos. That means even if an electron neutrino got converted into a muon neutrino, I will still detect it. And when they detect that one in Canada, they found the exact match. So the puzzle got solved, and in the process, we got the new physics, that is neutrino oscillation.
Thank you so much, sir. I guess there are no further questions from the students.
Can I just add one thing?
Yes, sir. Sure.
Whenever there is any puzzle, there are multiple suggestions for that. For example, when there is a beta decay was there was a suggestion that energy conservation may not be true. But somebody suggested, okay, there is another new particle is formed, which is neutrinos. So when you say, okay, I mean, if Bette's theory was wrong about how solar energy is formed, is correct or not, okay? That was a question about that too.
Thank you, sir. And if I may ask one question, so I'm not a person of energy physics background. So just one question that Rick, Ellis, and Fair, apparently it seems that they're addressing the same physics questions to understand the phase transition between this hadronic bound state and the QGP phase. So I know it's oversimplification. So I wanted to know that what exactly is the need for 3 different experimental setups?
Good question.
So you said Rick, Alish, and Fair. Yeah, I think
Without having much understanding of
Yeah,
energy
no,
physics
that's-
background,
that's-
very naive question, I
That's
know.
okay. I think the question is formulated nicely because RIC is an accelerator facility, FAIR is accelerator facility, but ALICE is an experimental facility. And that is in LHC, but you are right because ALICE only looks at heavy ion. So in that sense, all 3 are heavy ion physics. So we collide either lead on lead or gold on gold and create this microsecond whole universe quark-gluon plasma. The main difference, let me first talk about difference between RIC and ALICE. RIC energy in center of momentum is 200 GeV and ALICE energy is 5.5 TeV. So in that sense, ALICE looks at very higher temperature, which is closer to the early universe. The early universe was hot and then it started particle. So in that sense, RIC and LHC you can club together. Only difference is that they are of different temperatures or different energy. FAIR is completely different. FAIR, like I showed in my picture also, you can create this quark and gluon soup in 2 ways. One is that you pump up a lot of energy, which will create a lot of particles, and ultimately it will look like a soup, which is the high energy or high temperature. There's another way is that inside 1 proton, if you put 5 protons, then the density goes up and it creates a neutron star. So core of neutron star is also similar. So in that sense, FAIR is looking at neutron star-like quark-gluon system, and RIC and LHC are looking like early universe-like quark-gluon system. So these are the 2 big difference. One is high density, and another is high temperature.
Thank you, sir. And you were just, okay.
Addition to this, both RIC and LHC are exclusively particle physics accelerator facilities. FAIR, on the other hand, is actually 4 accelerators rolled into 1. Okay. Only one part of it is the dense matter physics. The others are electromagnetic interactions at very high field strengths. So FAIR has several other aspects, and it has 4 different projects in it. Didn't have time to get into the actual description of FAIR, but I'll just mention the names of the 4 projects. One is New Star, which is nuclear structure and astrophysics and nuclear reactions. One is APA, okay, applied physics, applied plasma and atomic plasma and physics, plasma and applications, which also includes biophysics and medical physics. Okay. Then CBM, which Dr. Chattopadhyay just talked about, condensed baryonic matter. And the 4th is PANDA, which is hadronic interactions at very high luminosity. Okay. So these are 4 different aspects, 2 of which are high energy related. One is material science, plasma and applications, mainly medical. And the 4th is neutron star physics, but nuclear reactions and origin of heavy elements and so on.
Thank you so much, sir. If I may ask one question regarding the INO project to Professor Mondal, or anyone else can answer. So the project is regarding neutrino mass oscillation. I mean, other countries are also doing experiments, China, Japan, they're also doing experiments on neutrino mass oscillation. So what is different regarding this particular Indian project compared to there?
Very good question. So yes, absolutely right. There is an experiment coming up in China, who is also looking into this this hierarchy problem that we want to do. And even Fermilab experiment Dune that is coming up that is also do. Okay, so there are two separate parts I will answer. First of all, we proposed this experiment much earlier, and if we have not had this problem, we would have got the result by now. So that is one thing. Second thing, the experiment itself is unique in the sense here we will be actually the neutrinos mostly going through the earth core, and that is what is there is another phenomena that is happening called earth matter effect. Okay, the neutrinos because of the high density of the core, their properties will change, and in addition to finding this mass hierarchy problem, we'll also probe the earth matter effect that is through neutrinos. That no other experiment will be able to do that one.
So in this way, that's different.
That is a different question. And in the process, actually, now many of our young colleagues are writing paper. Now they are actually, there is a conference actually dedicated is happening to understand the earth core through neutrinos. And that's actually a new subject is coming up, where geologists and the neutrino physicists are working together to understand that. And for that doing, you need an experiment like INO, where the neutrinos will go through the earth core.
Okay, so while doing this, did you face any particular technological challenge?
Yes,
apart
I
from
mean,
the political challenge that you already
no,
mentioned
so,
in the beginning.
so actually, so good question. So at the beginning, when we proposed this experiment, that was our nightmare, because we are talking about these new technologies, and each of them we have to invent, actually, you have to build. And so we actually, we got encouraged because we talked to different kinds of experts, the electronics expert, detector expert, and they all told us that, yes, we will be building it. And that time that's a promise. I would say 15 years back, it was just a promise that they'll build it. But if you look at today, yes, we have gone through challenges, but one of the challenges was happening actually that detector that we are building. This is a resistive plate chamber detector. Subhashi knows that well. He has worked on that for quite a long time. And is that proper coating of the glasses and then make it big size? Actually, each of the detector is 2 meters by 2 meters. And then what kind of coating is required? So interaction with industries. And we managed to, so there are hurdles, but slowly we have managed to do that. The design of the chips, actually. And we started with the design level, make the ASICs and build it all together. So those challenges are there in our problem that whether we'll be able to overcome. But I am happy today, if you go to Madurai today, a prototype of the detector using all those technology that we wanted to promise to develop, they are all working together. So that we have overcome actually. But it was a big challenge certainly. And that's the idea actually. That is how you should be doing science. And you take those challenges and then develop technologies that will overcome that. All high energy physics experiment anywhere in the world is doing that. There is nothing
Thank you so much,
particular
sir.
about
I
us.
just want to add one thing that I do not know about political problem when I know when on or where I know will come, but the technology that we have gathered together on the detector front, I think it has many more applications, which we can, one example we can talk about where this thing is being talked about, and there are activities which is called muon tomography. You know, a lot of muons are coming through you all the time. Now, in border, if a truck goes and inside that there are some contraband like uranium or something, and there is no way that you can take pictures of X-ray and find them. Now, what is being done is that the detectors, which Professor Mondal said, 2 meters by 2 meters, if you make arrays of detectors on the top and bottom, and then your truck goes through it, muons will pass through the detectors. And if there are some materials which are high jet like uranium, those muons will bend. And the detectors, if it is sensitive enough, then you can even know without doing anything that there are something inside this. So similarly, there are medical applications as well. So if you just for the time being forget about INO project, but then detector development itself, in my opinion, is certainly a capacity building for the country.
Wonderful. Wonderful. And one question to Professor Banerjee. So, sir, it's a very naive question from my end. That discovery of Higgs boson is definitely a huge success. But is there any gap between the theoretical predictions and the experimental observations? Was there any gap in CERN?
Well, the thing is, okay, you're talking about just this Higgs boson. For Higgs boson, we have not seen any deviations. For other things, we see deviations, but not at the same level as what is see, okay, as a discovery. You see at the level of 1 in 100.
In fact, in other cases as well, I'm talking about the
1%
project as a
difference,
whole.
which has 1% probability, which is called a 3 sigma effect, but not a 5 sigma effect.
So thank you very much. My heartiest thanks to all the esteemed panelists and to all the students I know.
Actually, Professor Bhattacharya has
Oh, sure, ma'am.
Already discussed what I want to know from Professor Mondal. I just want to know, is there any upper limit on the mass of the neutrino? Because if neutrino come massive, then it has some implication in the total mass of the universe. So if you put some light on that.
Yeah, there is upper limit on the mass of the neutrinos, and that is coming from, there is experiment. So there are two kinds of experiment is going on. One is to measure the mass hierarchy, which one is heavier, and these neutrino oscillations, we have only seen the mass square differ. You know, what is the mass square difference?
M square, actually,
but not the absolute mass. For doing separate experiment, the endpoint, basically, if you look into the beta decay endpoint, that will give you what is the neutrino mass. So there are certain experiments going on to measure actually the neutrino mass from there. And from there, we have now the upper limit on the neutrino mass coming from there. Also, we get the upper limit from the astrophysical studies also. So that is there.
So we have three kinds of neutrinos, I mean, three flavors. So tau neutrino is the massive, most massive. It is the assumptions or?
No, that is, now this is another thing. So when you say tau neutrinos, it's not the mass eigenstate. Okay. So tau neutrino, electron neutrino, mu or neutrinos, these are the flavor eigenstate.
Flavor eigenstate.
So
Yes.
so tau neutrinos is a mixture of all three mass eigenstate. Similarly, electron neutrinos is also a mixture of all three.
So that's why you take the treatment for 2 generation and 3 generation like that, right?
I mean, yes. Yeah. I mean, no, that is the difference. 3 generation, 2 generation is 2 generation. If you take it, is simpler to do your calculations. But then 3 generation, when you put, then it's difficult. So that's a different question. But mass eigenstate, tau neutrino is not the mass eigenstate.
Okay.
Okay.
It is flavor eigenstate.
It's a flavor, but it's a mixture of 3.
So what is the mass of this one? I mean, upper limit, like the maximum mass? Do you have any idea?
So right now, the upper limit around 1 electron, less than an electron volt or so around. I don't know if there is, I mean, latest number that is coming from the
So it is in the order of electron volt like that, right?
Yes, at the moment.
Thank you, sir.
Thank you so much, ma'am. Thank you so much.
Just I have one question.
But there's one
Sure,
thing, okay? This is only talking about three generations neutrinos, okay? But there could be other neutrinos which could be stellar neutrinos, okay? I mean, which is sterile neutrinos, which is not there, okay? I mean, people are still looking for them.
But there is actually this constraint is coming more and more there. See, the main result came from this Los Alamos experiment, and that was doing on that. I think that is getting constrained a lot also now. It's the sterile neutrino part. No, many people are actually doing, and Praveed and DP, and in India, actually India, the theoretical neutrino physics group is very strong actually. I mean, there are lots of people are. There are people who wanted to look into sterile neutrino, but yes.
Sir, I have one question. Actually, in these mega physics experiments, whether it is in LHC or other FAIR and other, so there must be some significant role of material scientists or engineers, and there must be some challenges faced by them. So could you share something with us? Thank you, sir.
No, no, even in India, okay, I mean, when we started doing the CMS experiment, one of the detectors which we trying to build was building the silicon strip detector. And obviously making a silicon strip detector is not just a work of high energy physicists, it is a work of also material sciences. So people from IIT Bombay, okay, was hired by BRC to really try to see, okay, how one can make strips on the silicon, okay, how to really process the silicon to have those things made. And that's how, okay, I mean, we made the first silicon strip detector, okay, for CMS experiment. And a byproduct of that was they tried to develop many detectors which are used in the, what do you call, the airports, okay, for security purposes. The same technology is used for that. So I think there is a very big role of the material scientists, okay, for building detectors in high energy physics.
Yeah, engineers, I think they're everywhere. So when you conceptualize the project, there is some role of physicist. And when you analyze again, they come back. But in between 25, 30 years, they're only engineers. You won't even allow to go there inside, talk to them, because they will have to build this 11,000 tons beast and then to move them, take data and all. The engineers are there everywhere. If you go to CERN, yeah, if you go to CERN, there's all these huge IBM or HP or all, they are there around because the CERN is their biggest customer. Now, about material scientists, I'm telling you, this again is the source of invention of new materials. Because you are talking about an environment which is the most harsh environment so far as radiation is concerned. And this is similar in space maybe. So if you want to use or develop materials, then you have to test it here. You have to work here. So that way material scientist even means has a very, very big role to see that which material works or not. There's another example I'm talking about, which is practical now, which Dr. Mondal talked about, a gas detector called RPC, resistive plate chamber. It's a gaseous detector. So there is some kind of gas which goes inside. When a particle passes through it, it ionizes it, and then you put a high voltage, it multiplies, and then you get a signal. The gas which is used is freon. And you know, freon is not environmental friendly. So it was changed once upon a time to something called R134, which was called environment friendly freon. And now that is also going to be banned. So now this RPC community is spending all their day and night to find another gas where environment friendly index is low. So this is something before we do any high energy physics. So their material scientists and engineers has much bigger role in my opinion.
The other place where the material science is extremely important is this development of the scintillating detectors. So we try to have scintillators which are very fast, radiation hard, and produce enough amount of light. And again, okay, I mean, that is a place, okay, where material scientists and high energy physicists, okay, they really collaborate to try to get them.
Thank you so much. Now, I think we should stop this Q&A session, although I know there must be some other questions, but it's over 5 p.m. now. So let's thank a big round of applause for all our esteemed panelists. And I would also like to thank from the bottom of my heart to all the students. I know some of you had to go home early. You had already told me, but still you were here. Thank you so much for that. And now I will hand over the session to Dr. Shatrupa Biswas for concluding. Shatrupa.
Thank you, Dr. Day. So we have come to the end of this program, and I'm filled with immense gratitude for our esteemed panelists and each one of you who have joined us today. The insights and discussions we had during this session have been nothing short of extraordinary. So we have gained a deeper understanding of India's significant contributions to some of the most ambitious projects in physics, and we have witnessed the dedication and passion of our panelists in advancing scientific research and collaboration. So now we have come to the end of the program, and now it is time to announce the winners for Fusion Diverse, that is the essay competition that we had on India's participation in mega projects of physics. This is the same topic. So this competition has been a platform for young minds to showcase their knowledge, insights, and creativity in understanding India's contribution. So we received an overwhelming number of exceptional entries from participants across various educational institutes, and the judging process was certainly not an easy task. So each essay displayed a profound understanding of the project, of the subject matter, and a genuine passion for unraveling the mysteries of the universe. So before I announce the winners, I want to extend my heartfelt appreciation to all the participants who took part in this competition. Your dedication to exploring India's role in global physics projects is commendable. And you have truly enriched this event with your contributions. Now, without further ado, let us celebrate the outstanding achievement of our winners. So in the third place, we have Anik Bhattacharya from Adamas University. Do we have Anik here? No? Okay, so his essay eloquently highlighted India's significant contributions to facility for antiproton and ion research. So Anik is now not here. I'll go to the second place. So in the second place, we have Muhammad Farhan from St. Augustine Day School. So do we have Muhammad Farhan here? He's also not here. Yeah, so his topic was on the Laser Interferometer Gravitational Wave Observatory project. And the third prize, the first prize or the winner of this competition is Shomosri Chatterjee from GD Goenka Public School. And her essay was on the topic of 30-meter telescope project. So is Shomosri Chatterjee here? She's also not here. So congratulations to all the winners, and thank you all participants for making this essay competition a success. Your engagement in the subject matter highlights the bright future of physics in India, and we are eagerly looking forward to witnessing your contribution to this scientific community. So now I would like to call upon Professor Dr. Moumita Mukherjee to give away the vote of thanks.
So very good evening to all of you. Finally, this is the concluding session. For last 2 days, we have gathered knowledge in the field of physics, not only in the field of physics, but also associated fields, how physics is connected with different corners of technology and other branches. Okay. So this is now the time to conclude the program. So Physics Pulse, organized by the Department of Physics with the theme that one should learn basic science to excel in applied domain. So this was our theme to organize this program actually. So if you learn basics of physics in depth, you can excel in every field of in all fields of technology, data science, medical science, nanoscience, technology, from micro to macro, everywhere. And even it is connected to other domains, say finance, law. So in different way, a physics graduate can go. Now, this is because you should develop your logic sense, your analytical power, sharpness in observing a particular object, then only you will get success in applied domain. So since you are on verge of completion of your class 12 examination mostly, so don't select a specialized subject from in the graduation level. Better you go for basic science, and after that, specialized subjects. Because it will help you to become a specialist. Otherwise, you will become a technical person, a technician, but not a specialist in your field. So we are thankful to Department of Physics for organizing such a good event, and very contemporary topics are covered here. And we are thankful to the head of the department and all professors there. We are thankful to Honorable Vice Chancellor and Chancellor for giving us the chance to organize this program. And particularly, I am very much grateful to all the speakers. We are thankful to them because they have given their time to share their knowledge, to share their ideas with the budding researcher, budding physicist in last 2 days. And we are thankful to everyone, and let's hope in coming year also we'll be able to organize such a good event that will actually help the students, and not only the students, the people who will get idea that we should go for learning physics, learning mathematics, learning chemistry. These are the basic science, and without basic science, we will not be able to excel in life. So thank you very much.